very good.
The danger is that it might disconnect. So, okay, so if it disconnects,
it might disconnect.
Rejoin.
Okay, so the first talk is by Shahab Yudaki on testing gravity on cosmic scales. So please proceed, because you know we are tight in time.
Sounds good. I'll just jump straight into it. So this is an analysis together with Pedro Ferreira, Nelson Lima, and Hans Winter. Let's see. So I'll start off by asking the question of why we want to explore modified gravity. So we want to test the laws of gravity, not just on solar system scales where GR has been well established, but also on cosmic scales up to 15 orders of magnitude larger than the solar system scales. We know that the universe accelerates, but we don't have a good model for what's causing this acceleration. So the cosmological constant has fine-tuning coincidence problems. And we're also experiencing tensions between different cosmological data sets. And we don't seem to have an obvious candidate that would resolve these tensions. So on the left, we see an example of this in the essay, in terms of the essay tension between imaging surveys such as DES, KIDS, and HSC with the Planck CMB. And on the right, you can see the tension in the Hubble constant between that obtained from direct measurements by Rees et al. As compared to the Planck CMB and even other combinations of probes such as BAO plus BVN. In terms of as we try to explore new models, we need to be clear on what the requirements are for a new model. So we want our new model to bring about concordance between probes. So ideally, but not necessarily, this would the model will be able to bring about concordance among all probes. In other words, resolve both the SH and H naught tensions. We want the model to be favored in a model selection sense. So this implies being favored from the point of view of the Bayesian evidence, the goodness of fit, or even better, the deviance information criterion, which accounts for the penalty of introducing new parameters. We also want the model to exhibit greater than 5 sigma deviation in the additional parameters of the model. So if we're introducing, for example, an equation of state, and we claim that this is alleviating tensions, that we would like to see the equation of state to be different from the fiducial expectation. And then we want the new model to stay robust when confronted with additional data. And so I'm showing an example here of a model that was not able to satisfy the first 3 criteria, but was not able to satisfy the 4th criteria. So I'm showing you on the left constraints in the sigma mega matter plane for KIDS and Planck. In lambda CDM, you find the constraints given by the dashed contours. And then in an evolving dark energy universe, given by the W naught WA parameterization, we find the solid contours. So in this extended model, the Planck contour sort of entering into the region of the KIDS contour. And so that's great. But then when we consider the 3x2 point analysis, so adding a galaxy lensing and galaxy clustering data in addition to cosmic shear, we were able to measure the matter density much more tightly. And so now in the plot on the right, we find that the Planck contour in red is sort of missing the 3x2 point contours. So this is an example of a model that was good for a subset of your data, but not for all of your data. And so looking at modified gravity, there are 2 approaches that we can take. One is a model independent approach, where we, for example, consider a G matter G light parameterization that modifies the 2 metric potentials psi and phi. Or you can also consider the index gamma modifying your linear growth rate, or you can consider Hondesky theories, so these are scalar tensor theories, a subset of stable scalar tensor theories, which are parameterized with the alpha I parameters, so alpha 1 to 4. And then you can also consider taking the ratio, for example, galaxy-galaxy lensing with the galaxy velocity cross correlations, and in that way divide out the galaxy bias and consider having a quantity that's more sensitive to modified gravity. So this would be the EG parameter. The second approach is the model-specific approach, and so here it's as the name says, we constrain a distinct model. And examples here include Jordan-Brzezinski gravity, general F of R, DGP, degenerate high order scalar tensor theories, non-local gravity, and bigravity. So why would we want to take the model independent approach? At the 0th order, all we really care is to search for any deviations from GR. So we don't necessarily care whether it's this model or that model. That's the true, that gives the true description of the universe, but rather, can we just rule out GR, or can we verify GR to increase in precision? And then the model independent approach also allows us to simultaneously constrain large classes of models. So instead of taking a piecemeal approach, you're taking a sledgehammer approach, which can be appealing. Now, why would we want to consider a model-specific approach? The model-specific approach allows us to simulate the theory of nonlinear scales. And by including these additional scales, we can increase our constraining power. The model-specific approach also allows us to change both the expansion history and the growth of perturbations in a unified way. In the model-independent approaches, we commonly just fix the expansion rate to the lambda CDM expectation, and we just look at the impact of the growth. But in the model-specific approach, these two come in a single package, and it allows us to resolve multiple tensions in an easier way. So it allows us to resolve both H0 and SA tensions. So here's an example of a model-independent test of gravity. I've introduced the Q and sigma parameters, where Q modifies the Poisson equation and can be thought to give rise to an effective gravitational constant, and sigma modifies the gravitational deflection of light. So here I've divided the Q and sigma parameters into 2 bins of scale and redshift each. So we have 8 additional degrees of freedom. And in the plot on the left, you can see that going from the lambda CDM contours in dashed to the modified gravity, to the contours in your modified gravity universe, is the sigma mega matter plane, you can resolve the tension between the 3x2 point probes and the Planck CMB. So the Planck CMB is in red, and the 3x2 point is in cyan. And I don't want to go into specific details on this. On the right, I'm showing you constraints for a specific combination of these extra degrees of freedom. But what I really want to do is go to the next slide, which shows you the full modified gravity subspace. So if we're varying the standard cosmological parameters, and we're varying all the systematic parameters, and this is just the triangle plot in the modified gravity subspace. So we're including large scale cuts because we can't capture we can't model the nonlinear scales adequately, and we find complete agreement with GR. So the GR expectation is given by the intersection of these dashed lines, and all the contours agree with GR. So the sign is Kiss plus Planck, and then brown is 3x2 point plus Planck. And because we've introduced 8 additional degrees of freedom, even though we've resolved tension in SA, this model is not favored in a model selection sense. So that's just a taste of the model independent type of test of gravity we can do. So let's go to the next slide. So and then turn to our model specific example. And the example we're going to be considering is Jordan-Brzezinski gravity. And the action for the Brzezinski gravity is given at the top, where we have a scalar field, which is multiplying so we have a new scalar field, which is multiplying your Ricci scalar, and we're introducing a coupling constant, omega Brzezinski. And then there are these additional terms which are written down, but I'm not going to go into great detail here in the interest of time. What I'll say is that we then vary the action with respect to the metric and with respect to scalar field. The former gives us the Friedmann equations, and the latter gives us the equation of motion of our scalar field. So we can see that for slowly evolving scalar field, where phi dot is close to 0, the expansion history behaves like similar to standard GR, but with this extra 1/5 term. And then from your equation of motion of the scalar field, you can derive how the scalar field behaves in the radiation dominated epoch, in the matter dominated epoch, and in the vacuum dominated epoch. And then again, I don't want to go into great detail here, just to say that the scalar field has an effect throughout the full evolution of the universe. So we're not introducing a new model that just gives us a specific behavior at late times, but this really is affecting all times. So for this model, it also gives us a modified Poisson equation, where G matter is our effective gravitational constant, and it goes like 1 over the scalar field times a product of the coupling constant, a function of coupling constant, and we're going to be considering two types of Jordan-Bernstein gravity. One is a restricted type where we just vary the coupling constant and we fix the effective gravitational constant at the present to be given by the GR expectation, which is 1. And then we have an unrestricted type where we vary both the coupling constant and the effective gravitational constant at the present. So there's a difference between having a 1 parameter extended, so an extended model where we choose 1 extra degree of freedom versus 2 extra degrees of freedom. And we can look at the perturbation equation for this model. So the way that the coupling constant affects the expansion rate is to slow it down. So this enters a friction term, and which leads to an enhancement of your growth. And similarly, the source term is also giving us an enhancement of the growth. But it of course depends on whether the effective gravitational constant is greater or less than 1. And then we can introduce a gravitational slip given by the ratio of our metric potentials. And if this slip, for example, varies with time, then we would rule out not just GR, but we'd also be ruling out all of Jordan-Bernstein. So why would we want to explore this specific model? I'm going to be using it as a test bed for cosmological analysis and modified gravity, and extended cosmologies more broadly, given its rich history, and the role it plays in some of the fundamentally motivated extensions to the standard model, such as string theory. It is in a meaningful way the simplest modified gravity theory, and it approximates a wider range of scalar tensor theories on cosmological scales. It is one of the remaining viable theories after the Ligo-Virgo measurement of the speed of gravitational waves. And we're going to be using this model to simultaneously constrain and explore the degeneracies between modified gravity and neutrino mass invariant feedback. And we're going to use it to see whether we can alleviate tensions. So I'm going to skip these slides. Here I'm showing you the impact of Jordan-Bernstein gravity on our expansion history on the left. In the middle, we have the Whale power spectrum. This is the power spectrum of the sum of your metric potentials, and then the CMB power spectrum on the right. And so we can see, given the equation I'm writing here on the bottom, we can see that as we increase the effective gravitational constant, we're going to be boosting our expansion rate, and that's what we see in the plot. And as we modify our coupling constant, it's going to give us a suppression in the expansion rate. In terms of the Whale power spectrum, again, the sum of the metric potentials goes like one of your scalar field. So again, you're going to be boosting the Whale power spectrum as the effective gravitational constant is greater than 1. It behaves somewhat differently on nonlinear scales. But you can see that this can compensate the effect of, for example, neutrino mass, which is given by the solid dashed black line here, and then we can also compensate the impact of Bernoulli feedback given by the dotted red line. And then in terms of the CMB, an effective gravitational constant greater than 1 is actually giving us a suppression, and it's increasing with scale. And I'm going to talk more about that here. So this is quite interesting. The main way that the small scale CMB is affected, the main way that the damping tail of the CMB is affected is through the ratio of the scale of your diffusion damping and the sound horizon, and that in turn goes like that is sensitive to the square root of your expansion history and the number density of free electrons. And in standard GR, you can show that this goes like that this is proportional to your effective number of neutrinos and the primordial helium abundance. But as I've shown you in the previous slide, the expansion rate goes like the square root of my effective gravitational constant. So we're going to get a similar effect from the effective gravitational constant, and we can see that it actually introduces a degeneracy with the effective number of neutrinos, but in particular with the helium abundance.
We have 3 minutes.
Okay.
3 minutes.
So you can see that given by the effective gravitational constant in the dotted red line, the red lines, and then the helium abundance given by the dashed blue lines. And I'm happy to talk way more about this. And so this might actually complicate our inferences of small scale physics with future CMB probes in terms of the uncertainty in the gravitational theory. So we further use numerical simulations, a hybrid suite of numerical simulations to quantify the impact of brand-cyclic gravity on nonlinear scales. And you can see how well we are able to model it. So we modify our fitting function based on the numerical simulations, and we compare it to the actual numerical simulation. We find a good agreement. We then use this to constrain cosmology. So I'm going to, given in the interest of time, I'm going to skip just the final results. So we can combine existing probes of the large scale structure, the CMB, and low redshift distances to constrain this model. So you can see that given by the black contour, and then the yellow contours are the ones where we fix the neutrino mass. And you can see here in particular in the S8 H0 plane that as we go from lambda CDM given by the pink contour to the extended cosmology, as we're increasing our effective gravitational constant, this allows for larger values of the Hubble constant, and it also allows for smaller values of S8. And we constrain the effective gravitational constant to the 3% level. We constrain the coupling constant to be greater than 2000, 95% confidence level. And even though we fully resolve the S8 tension and we bring the H0 tension down by about a sigma, from the model selection sense, in terms of the deviance information criterion, this model is not favored relative to GR. And I'll just end with this slide, which is that the constraints on cosmology do depend to some extent on our specific parameterization of Jordan-Brzezinski theory. And so here I'm considering four different types of parameterizations. And the plot on the bottom right, I'm showing you constraints in the plane of the sum of neutrino masses and the bearing feedback, the x-axis, for these four different types of modified gravity parameterizations. And so you can see that as we go from a fiducial parameterization to other parameterizations that allow for stronger modified gravity, this can degrade or constrain on sum of neutrino masses by up to a factor of 3. So this plot here kind of nicely ties together the sum of neutrino masses, bearing feedback, and modified gravity. So just to end here, I've considered an end-to-end exploration of distinct modified gravity theory, both from an analytical point of view, from the point of view of numerical simulations, and then taking this to cosmological constraints from existing probes. I provided simultaneous constraints to modified gravity, mass neutrinos, bearing feedback for the first time. We can partly resolve cosmic tensions, but even so, this model is not favored in a model selection sense. A positive shift in the effective gravitational constant suppresses the CMB damping tail, which can complicate future inferences of small-scale physics from the CMB. And then we expect an order of magnitude improvement in our constraints on modified gravity, in our constraints on Jordan-Brzezinski gravity with stage 4 surveys. And this will allow for comparable constraints on this specific model of gravity from cosmology and astrophysics. So I'll just end there.
Okay, thank you very much for this nice talk. So it is time for
and I skipped a lot of content. So yeah, there's
yeah,
much
in fact,
more. Yeah.
Okay, but we are exceeding a little bit the time. So
no, perfectly fine.
If there is any question or comment at this point, please.
Yeah, can I ask a question?
Yeah, Nick. Yeah, sure,
you.
Nick, go on.
Thank you. A very nice talk. Thanks very much. I would like to ask how you compare your measurement with the Lyman alpha series of the measurements of the gravitational constants and other tests. Are they more accurate?
So we did not include the Lyman alpha. So the Lyman alpha would take you to a larger redshift, and you potentially go to smaller scales. So definitely that could help to improve your constraints. But I think one really crucial test is asking, is the constraint, sorry if I can scroll back, is the constraint I'm getting here? So
yes,
0.996.
that's what I want, this value. Precisely.
So the question we want to ask is, this is the constraint at the present. This is the constraint of the effective gravitational constant at the present. So you might want to ask, is this consistent with the early universe? So we know how to propagate. So because there's a unique theory, so we can take this together with the constraint of the coupling constant, and we can ask, what is the effective gravitational constant at the BBN epoch? And that is 0.99 plus or minus 0.03. And that is consistent with some of the direct constraints on the gravitational constant from light element abundances that people have been getting. So the constraint we're getting at late time is not breaking any consistencies with constraints obtained at earlier times.
Thank you.
Okay, thank you. So, as you know, we did also a similar analysis of Brans-Dicke theory recently. I wonder how many parameters, extra parameters are using you apart from omega BD. Did you use the initial condition, for example, for the Brans-Dicke field at very high redshift? Did you?
No, so that is the, so you determine your theory at late times, and then that has implications for what the theory implies at earlier times. So that's kind of touching on what I said about the BBN. We can take the late time constraint and translate it into earlier times, but we only have two parameters. So, well, in the restricted case, we have one extra free parameter, and in the unrestricted case, we have two extra free parameters. And then we're varying all the standard GR, so all the standard Lamissian parameters. Then there are all the systematic uncertainties that go into the kids analysis, the BOSS and CM. So yeah, it's a combination of systematics, standard GR parameters, and then one or two extra.
But the specific Brans-Dicke parameters are just omega BD or anything else?
So just omega BD and the effective gravitational constant today. Those are the two extra Brans-Dicke parameters. Everything else is fixed by the theory.
Okay. Thank you. All right, so I think we have to move because we have a tight program. So thank you very much again for your contribution. So now I would suggest Matteo Luca to share the presentation, please.
So I hope you can see my screen.
Yes.
All right. So first of all,
please go on. Yes.
Yeah, thank you very much. Thank you very much for being here, although unfortunately virtually. And thanks also to the organizers for the understanding in the timing of my talk, and also to Lilia, if that's pronounced correctly, for accepting to swap the timing. All right. So as you just said, my name is Matteo Luca. I'm a PhD student at the Université Libre of Brussels. And in this talk, I will try to discuss a specific model of dark matter dark energy interactions and try to place it in the context of cosmological tensions. The work I'm going to present is based on these two papers, the first one in collaboration with Diana Hooper on the Hubble tension, and the second, more recent, on the sigma tension. But all right, diving directly into the model, the idea here is that when you assume dark matter dark energy interactions, the main difference with respect to the lambda CDM scenario is that the continuity equations are not conserved singularly anymore, but are coupled via an energy transfer function, which I will refer to as Q. And ideally, you would want to derive this function from first principles, but as it turns out, this exercise is not as easy. One way to see it is, for instance, going from particle physics and defining two fields, phi and psi, the first one being the dark energy, the second one, the dark matter. And then in full generality, say you can define the potential of the dark energy and a mass function for the dark matter. The mass function also includes possible interactions between the dark matter and the dark energy, which can be either linear, exponential. There's, as I said, a very large freedom. And then it can be shown that the transfer function Q is a function itself of V and M. And so intrinsically inherits the freedom that you have in the model building. And of course, this is just one way of seeing it. You have just seen that there are many possibilities also coming from modified gravity to derive this sort of coupling function. So really take this as a justification for why Q is really hard to pinpoint to a precise, let's say, with precise features. However, at a cosmological level, what you would like to do is, which to me also makes sense, is to assume dependencies on the energy densities of the two fluids involved in the interaction, so the dark matter, the dark energy, and on the Hubble rate. Now, in the many possibilities and combinations of the energy densities have been investigated in the literature. Personally, one option that I find particularly interesting because of its stability and success is the one that involves the dark energy density. And as it has been pointed out in these references, Gavel et al., for instance, assuming the dark matter energy densities can lead to early time instabilities when you're not careful enough in the choice of the dark energy density or in the choice of your parameter. So in this sense, this choice allows you a larger freedom in the choice of the parameters. And also, to me, there is really the appeal of a clear cosmological meaning because you can assume the dark energy density to be so the equation of state to be close to the standard value, which simplifies the continuity equation. And then you can see that Q becomes a function of a derivative of lambda, which of course is a constant in lambda CDM, and therefore you have no energy exchange. But if you assume a very simple dependence of lambda on the redshift with a new free parameter psi, then you end up with the same functional form of Q that I argued for at the beginning. Now, let me also drive home the point that at least in this particular setup, it is important to differentiate whether Xi is positive or negative. And you cannot just run your simulations on on any value of Xi, because there are really phenomenological implications for whether Xi is positive or negative. And in particular, if Xi is negative, the energy transfer function, like the energy itself, flows from the dark matter to the dark energy. And when Xi is positive, it flows from the dark energy to the dark matter. So there are really energy scales involved and decaying channels that are completely different depending on whether Xi is negative and positive. So despite the fact that the mathematical setup is the same, I will try to differentiate the two models and treat them as separate. Now, said that, let's try to understand some key features of the model at the cosmological level. In particular, if Xi is negative, as we said, when Xi is negative, the energy flows from the dark matter to the dark energy. So you expect more dark matter in the past with respect to lambda CDM, because you have energy flowing from the dark matter to the dark energy. So if you fix the energy densities today, you need to have more dark matter in the past because of the flow it has towards dark energy. And the opposite is true, of course, for the dark energy, which has a decreased energy density in the past and increases as the dark matter decays into it. The opposite is true for the case where Xi is positive. So in this way, you have a decreased dark matter energy density because the dark energy decays into that. So it increases in time. two very straightforward consequences of this behavior is that when Xi is negative, for instance, the Hubble parameter during matter domination is increased and decreased if Xi is negative, is positive, sorry, and that the redshift of matter radiation equality shifts to the left or to the right, depending on whether Xi is positive or negative. And this will have key implications for the ability of the two models to address the tensions, as I will try to explain in this slide. So it is a bit packed, I understand, but focusing first of all on when the case where Xi is negative, we said the dark matter energy density is increased. So in order to preserve the goodness of the fit to the data, you need to decrease the value of the value today of omega dark matter. And by doing so, you can kind of equilibrate the change in omega C, in omega dark matter. But as we know, Planck measured the angular scale of the sun horizon. So this you want to stay fixed. And since what I'm talking about is a late time modification of the expansion history of the universe, you're also not really touching the sun horizon, which is the denominator of the angular scale of the sun horizon. So you want the last scattering distance to be almost unchanged as well. And the last scattering distance can be defined as in this equation. And the key function here to have a look at is the Hubble rate at late times, which can be defined in this way. And as we said, you can kind of correct for omega C, omega dark matter, by decreasing the value today. But still, if you have a high interaction rate, the dark matter energy density is going to decrease very quickly. So you can increase Xi, compensate for the increase for the omega dark matter, but still the dark energy will decrease in the past. And in order to compensate for the dark matter decreasing, you have to increase the H0 value. So in this way, the model allows you to address the Hubble tension. On the other way, if you assume Xi to be positive, what happens is that you have to kind of do the opposite. You have to increase the value of omega C to compensate for the decrease in the past. But you only need to do it to the point where the redshift of matter radiation equality is decreased with respect to lambda CDM. And if you do so, then you can also decrease the scale of the matter radiation equality, which directly depends on the corresponding redshift, and the amplitude of the matter power spectrum, in particular at very large K values, so that in this way, the model allows you to try to address the sigma tension. Now, starting from the first case, what we did was, so let's start by looking at the dark matter dark energy interaction and in respect to the Hubble tension, and try to see whether this model can really address the tension. And before going directly into the model, let me try to address some generalities that I think, at least to me, are important to discuss before going in the particular scenario I'm talking about. First of all, when looking at late time solutions to the Hubble tension, it's, to me at least, often unfair to only restrict yourself to CMB anisotropy data, because since the modifications at a very late time, the only effect is that to blow up the error bars of your model of the H0 value. And what you need is really an additional anchor at late time, some complementary data, which is normally BAO, and which normally comes from BAO and supernovae. However, these data sets have been shown to be strongly preferring lambda CDM over other possible variation of the expansion history. So this makes much harder for late time modification of the expansion history to be able to address the Hubble tension. There are, of course, exceptions. We've seen it yesterday with, for instance, Brandsticker theories. And so, but as a general rule, this tends to be the case. So we are really witnessing the emergence of a sort of no-go theorem for late-time solutions, again, with exceptions, but this is also something that has been discussed in David Wong's talk on Monday, where indeed it was a similar setup, what different choices for the energy transfer function. And coming to now to the model itself, what we tried to look at in our paper was whether this no-go theorem really applied to this setup as well. And as it turns out, although it's always kind of arbitrary to define when two datasets are incompatible or not, Here you can clearly see that the Planck contours, so the Planck constraints in red really are an explosion of the error bars, and to the extent where if you only add Rees et al., you could solve the Hubble tension, but as soon as you assume BAO and Pantheon 2, you see that there is almost no overlap. So it's kind of unfair to combine all the data set because they are not compatible. What you will find is a weighted average which fits none of the data. Okay, so this is something I would be more than glad to discuss later, but this is just a personal take. And moving on to instead the possibility that Xi is positive, so where the energy density goes from the dark energy to the dark matter. Just to recap here, the idea is that you lower the dark matter energy density in the past, so you decrease the value of the redshift of matter radiation equality and the corresponding peak of the matter power spectrum, which is related to the scale of matter radiation equality. And therefore you see that the amplitude, in particular at large scales, it's very suppressed when Xi is positive, and it is increased when Xi is negative. So comparing this to data, even including Planck, BAO, and Pantheon, which to me is the baseline data set, you see in red that the model is indeed very much able to address the sigma tension here.
3
to the
minutes,
point where,
Matteo.
sorry? Yeah, thank you.
3 minutes.
To the point where it becomes possible to combine the baseline data sets with, say, weak lengths in surveys or in general late-time measurements, which would otherwise be in tension. And if you do that, you end up with the orange contours, which really bring the tension between the early time inference and the late time measurements below the 1.5 sigma level. And let me also remark the fact that when Xi is considered positive, when you can solve the sigma tension, you do so without introducing no worsening any other tension. So the H0 value stays very much compatible with the Planck prediction in lambda CDM. And you also do not worsen the fit to the data. So, and this is, to me at least, rather uncommon, because also in the case where Xi is negative, you end up worsening the sigma tension significantly. And this is, by the way, also a behavior that David once pointed out when considering a similar model. This seems to be a general feature, but when addressing the sigma tension, it does not happen, and it makes, to me, this possibility very appealing. Now, this is roughly what I meant to say, and coming to my summary, the take-home messages I would like you to remember are that dark matter, dark energy interactions can be motivated at a very fundamental level, phenomenologically, as well as by modified gravity, but they come with a huge freedom in the choice of the interaction terms. A very successful choice and a very cosmologically meaningful choice is by introducing a dependence on the dark energy density. And this model, depending on the sign of Xi, which is, however, important to keep track of, it can solve either the H0 tension or the sigma tension. It cannot solve both, because as we saw, there is let's say, a contrast in the direction the parameters are going. But depending on the choice of Xi, you can solve either one or the other. In one of our papers, we make the argument that this model is unable to solve the Hubble tension, as well as many other late-time modifications. But if you assume Xi to be positive, then you really are able to successfully reduce the sigma value predicted by early-time measurements to the point where it becomes compatible with late-time measurement. Now, since this happens without worsening any other tension, nor the fit to the data, it is, to me at least, an interesting avenue to consider the fact that you could combine this model with additional interaction channels, for instance, photons that only affect the early time universe, and see whether they can, this multi-interacting model can address both tension. This is a possibility I considered in this paper, but unfortunately I have no more time to discuss about it. So I thank you very much for your attention, and I'm looking forward to any questions you might have.
Thank you very much, Matteo, just in time. So is there any question or comment to this talk?
Yeah, can I ask a question?
Nick, yes.
Again,
please.
sorry, I didn't see anybody
No
else.
problem. I mean, if you are first, you are first.
All right, thank you. A very nice talk. I was wondering whether if you consider other forms of interaction, for instance, including higher powers of H square in your dark energy, dark matter interaction, what would happen?
Yeah, that's a very good question. I am not sure I'm not aware of any study which considers higher powers. There are many that consider not only dark matter energy densities, but also combinations of them. Yeah. And my feeling is that every time you include something different than dark energy density, you run into trouble. So it's a very good question. I must say I haven't seen it, and I'm not even sure if there are, maybe there are some, the reason why there are none, it's because there is some intrinsic problem that I'm not seeing right away, but it's certainly something worth thinking about, in my opinion. So thank you for the question.
Thank you.
Okay. Any other questions? I just want to point out that I discussed this with David, actually. We obtained similar results when we assumed this kind of a scenario, but in order to improve the two tensions at the time, it's not enough just to play with these variables. It is convenient, or at least it is a possibility also to use the possibility that the gravitational constant is mildly evolving with time. And then when you do both things, where you allow both variables to change, then it is possible to improve the H0 tension, as you can see in a recent paper of us. Just a comment.
Yeah, I mean, and personally, unfortunately, I'm not sure I'm aware of the reference you're referring to.
I will send you, don't worry. No
okay,
problem.
Yeah, thank you very much.
I can send you.
And I would love
we need not
to
take time here. I will just send you, no problem.
Thank you very much. Okay.
Okay, so thank you very much for your talk. So the next speaker will be Colin Hill about exploring cosmological concordance with ACT, DR4, Planck, and beyond. So Colin, please, you can, yes, all right. So you can just start as soon as you like.
All right, great. Hopefully you can see the slides okay.
Yes, we can see.
All right,
so
perfect.
I can.
Okay,
So
well, first, great. First, let me just thank the organizers for the invitation. There's a lot of interesting things to digest. I'm enjoying the meeting so far. So I'm going to talk about this broad topic of cosmological concordance and exploring it with various data sets. And this is work with this cast of characters down here. Okay, so I'm first going to start out by reviewing the status of measurements from the Atacama Cosmology Telescope ACT, both in the context of lambda CDM, and then turning to some extended models. So I'll go through two different approaches toward resolving the Hubble tension. One focused on small-scale baryon clumping as potentially generated by primordial magnetic fields, and then this well-known early dark energy approach. Okay, so first let me start out with a quick review of where we stand with data from ACT. This is summarizing our two main cosmological analysis papers that came out last summer, which you can look to for much more details about what I'm telling you here. All right, so in case you haven't heard of ACT, it's located in the Atacama Desert in northern Chile. This is the ground screen around our telescope. There's the actual telescope itself inside. We've surveyed about half the sky now with ACT, basically everything that you can see from Chile. We've now obtained data at multiple frequencies, ranging from, well, we have good data from 90 to 220 gigahertz, and then we have a low frequency receiver that's on the telescope now, observing at 30 and 40 gigahertz. So 5 total frequency channels available soon. And we've been observing for almost 15 years at this site. Here's a picture of the group at our last in-person meeting a couple of years ago. So we've released a lot of data and analyses in the last year or two. I'm just going to focus on these cosmological analysis papers here, but I want to point out there's a lot of other interesting things you might want to take a look at, including component separated maps, for example, of the Compton Y parameter, which I worked heavily on, reconstructed gravitational lensing maps, as well as preliminary maps combining some of our more recent data with data from Planck in this paper by Sigurd Næss et al. So just to give you a flavor of the improvements that the ACT data provide, this is a patch of sky covering about 600 square degrees, first seen just in Planck at 143 gigahertz. Then here's what it looks like when we fold in the ACT data at 150 gigahertz. So if I flip back and forth between these, you can see that the resolution sharpens up immensely on small scales. And in addition, we can see these small scale features like radio and infrared point sources and the shadows cast by Synav-Zeldovich clusters. So there's a lot of additional information that you can access on small scales with ACT, in addition to much higher signal to noise measurements and polarization than what are available from Planck. So skipping to the things of interest here, this is our results for the foreground marginalized CMB power spectra in this DR4 analysis that came out last summer. So you can see the TT, EE, BB, lensing, and then the TE power spectra shown here. And to put these in context, these are other current measurements in the field. I think these are just missing the latest SBT 3G results, but otherwise these are pretty complete. So we have a pretty beautiful picture of the CMB power spectra over a wide range of scales in both temperature and polarization. So this is of course highly constraining on cosmology, which is why we've made the measurements. So ACT is getting to the point where it's now a completely independent check of both WMAP and Planck with relatively similar statistical power. Lambda CDM fits the ACT data quite well. You don't have to look at all these different posteriors, but the main takeaway is that these three experiments give generally very consistent results. Formally, it's consistent at the roughly 2 to 2.5 sigma level. And this means we can then combine ACT and WMAP to form a data set that has statistical power almost approaching the Planck data, but it's completely independent of Planck. So it gives us a test of any potential systematic that you might worry about from Planck. So this is what you get if you perform that combination. So ACT plus WMAP is in purple, Planck is in light blue, and then you can also potentially combine ACT and Planck, which is in dark blue. As you can see, everything here is in very nice agreement. We have a very consistent picture from these different CMB experiments. Obviously, the H-Naught panel is perhaps the one of most interest here, so I've zoomed in on that one. And you can see that ACT plus WMAP in purple gives a result that's very consistent with Planck in light blue. So this effectively rules out any systematics explanation for the Hubble constant from the early universe, which I think was already known given the fact that other data sets like BAO plus BBN yield the same result for H-Naught. This is a very clean confirmation. I'm not going to go through all these in detail, but we of course looked at a whole range of variations of our analysis to make sure the results are stable. They are indeed very stable, and you can find the details in these papers. So just putting this then in context, the ACT results are here in yellow in this whisker plot showing H-Naught results. The pre-ACT DR4 results from Planck, for example, are down here in blue. And then some of the local measurements just from the distance ladder are shown up here in purple. So you can see that we're quite consistent with the TRGV results from Wendy Friedman's group, but there is a tension with the Shoes results. Formally, with the latest results from the Rees et al. 2021 paper, it's about a 3.3 sigma tension between our result, ACT plus WMAP, and their result. Okay, so now let me talk about a couple of approaches toward potentially resolving this H-Naught tension that we've been looking into. I'm going to start out with this more recent paper that was led by Leander Thiel, a graduate student at Princeton, and Yilun Guan, a graduate student at Pittsburgh, as well as these other two familiar faces. So this approach invokes small-scale inhomogeneities in the baryon distribution as a way to potentially resolve the H-Naught tension. So let me explain to you how this works. So the basic idea is that we want to push recombination to an earlier time, such that the sound horizon is then smaller because it's at an earlier time. And then the H-Naught that you'll infer from the CB power spectrum increases. Now, this is the general type of decreased sound horizon approach that many different models have pursued. And the way this is achieved here is to note that there's a term in the recombination physics, the recombination rate here, which goes like the square of the electron number density. So if you induce large inhomogeneities on small scales in the electron distribution, you can take advantage of the fact that the average of the square is greater than the square of the average to get faster recombination, such that recombination happens earlier, and thereby you get a smaller sound horizon. So one could take an agnostic view and just put this into your Boltzmann code directly, which is what we did. Physically, probably the most well-motivated way to do this is primordial magnetic fields, which can dynamically sustain these large inhomogeneities that would otherwise be suppressed by diffusion damping. And the idea of this actually goes back almost a decade to work by Carsten Janamzik and Tom Abel. And then Janamzik and Pagosian pointed this out as a potential H-naught solution about a year ago. So just showing you how the mechanism works here. So this is the ionization history of the universe. Lambda CDM is blue or dashed orange. And then two different baryon clumping models are here in green and red. And all you should take away is basically just that recombination is being pushed to higher redshifts, as you can see by looking at the midpoint of the recombination process here. Another thing to note is that the width of the recombination process also changes a little bit, which means that the polarization power spectrum is going to have some non-trivial changes in these models. Okay, so let's zoom then to the results. So ACT is interesting in this context because it provides an independent test of this scenario with small scale CMB data, and it probes scales that Planck does not, as I showed you earlier. And we also have higher Snelton noise in the polarization fields. So here are the posteriors of just two parameters of interest in these fits. So H-naught down here, and then a one parameter extension that characterizes the amount of this small scale baryon clumping. If you're interested in the details of the model, we can talk about that later, or Livon might talk about this later in his talk. But the takeaway here that you can see, so first of all, Planck is shown in the dashed curves, and then when you add ACT in addition to Planck, you get the solid curves. The main thing to note is that the H-naught posterior just tightens up, going back towards lambda CDM, and the upper limit on this baryon clumping parameter just tightens up. So the independent modes that we measure in ACT on small scales don't seem to show evidence of the predictions of these baryon clumping models. And if you look at the actual marginalized results on H-naught, you can see that there's not a significant shift upwards. So there's not a major reduction of the tension with shoes, which means one should really be wary of combining the data sets, even in the context of this extended model. We considered trying to broaden the parameter space further by allowing additional parameters that characterize the small scale baryon PDF in these models. And without going into all the details, here it's characterized by just one additional further parameter. You can see that the posteriors on H-naught really still don't change even when you marginalize over this additional freedom. So just a quick summary of this work. We don't find that these baryon clumping models are preferred by the combination of current CMB data sets. We also looked at folding in BAO data. That did not change the story. So the inferred H-naught value is still in tension with shoes, even in the context of this extended model. If one does try to combine shoes with the CMB data in this particular model, you find that the chi-squared of the CMB data sets worsens by about 6 or 7 relative to the lambda CDM best fit. So it doesn't appear that the model has the ability to restore concordance, at least as currently formulated. We thought a little bit about ways you could extend the model to potentially help. Probably the best hope would be to introduce some time dependence in this small scale baryon PDF, which would be more realistic anyhow. But we haven't yet pursued this quantitatively. All right, so in the final chunk of my talk, I want to discuss a different approach towards resolving the H-naught tension using this early dark energy scenario. And this is work that came out last year. So I think most people have probably heard of this EDE approach, but let me briefly summarize it. The idea is to introduce some new field that briefly contributes about 10% of the total cosmic energy budget, roughly around the redshift of matter radiation equality, although that appears to be a coincidence in the current scenarios. And then rapidly decays away so as not to disturb late time cosmology. And the upshot here is that this new field quasi-accelerates the background and thereby decreases the size of the sound horizon that's imprinted in the CMB. So the same sort of qualitative approach as what I mentioned a minute ago, but achieved by a very different physics. So there's 3 new parameters introduced in these models. FEDE, which is the maximum fractional contribution that this field makes to the total energy budget, the redshift where that happens, ZC, and then the initial field displacement on its potential. And these are what I might call effective parameters. And one thing we showed in our work was that there's a very nonlinear relation between these and the physical scalar field parameters, and you can actually get rather different results if you formulate the MCMC sampling in the other parameterization. Okay, so of course, the reason people are excited about these models is that they preserve a good fit to the CMB data, as you can see here. So this black curve is the lambda CM model with H-naught of 68, and the red dash is an EDE model with H-naught of 72. And the fractional difference is shown over here on the right, and it's within roughly 1% all the way up to the range of scales that Planck has good signal to noise. What had not been investigated in great detail before our work was the effects of these models on the large-scale structure of the universe. So in particular, looking here at the matter power spectrum, these are for the same models that I just showed in the previous plot. You can now see that there's a difference by I, even on this log scale between those two models in the matter power spectrum. And if we look at the ratio over here on the right, you can see that there's changes on the order of 10% over a range of wave numbers that's well measured in current data sets. So this tells you that folding in large-scale structure data could have some serious impact on the ability of these models to restore cosmological concordance. So where does this change come from? It's actually really driven by the changes in the standard cosmological parameters that one needs to fit CMB data in these models. So in particular, if you look at the posteriors here from a fit to effectively Planck and a few other data sets, you can see there's a large increase in the cold dark matter density that's needed in this EDE scenario. And that's basically just needed to compensate for the early ISW effect that's introduced by this early dark energy. And then there's also a noticeable increase in the scalar spectral index, NS. And that's just to do, again, to compensate effectively for the suppression of perturbation growth due to this new field. So if you propagate this down to the S8 parameter, you get a non-negligible increase in S8 in the context of these EDE models as compared to lambda CDM. So you trade off a bit of H0 tension resolution for an increase in these S8 tension. So we then explored trying to fit these models to various data sets. And I'll try to just quickly summarize some of these results here. So this, what I'm going to show you is a fit to what we called everything at the time of this work about a year ago, but without including the local distance ladder measurements. So basically all the cosmological indirect data. So the EDE scenario is shown in blue, lambda CDM is shown in red. And if we just zoom in on the H0 panel down here, you can see that there's not a massive shift in the inferred H0 value. So there's a broadening of the error bars in this EDE model, given that has 3 additional free parameters, but there's no major shift in the H0 tension with respect to shoes certainly persists. One can then formulate this in terms of constraints on these new parameters. So FEDE is the parameter that characterizes how much of this early dark energy exists. And if you look at the analysis of everything without shoes, you get this blue curve here, so a strong upper limit, about 6%. And then in terms of H0, you can see the shoes is still in over 3 sigma tension with the other data sets, even in the context of this early dark energy model. If you do try to then fold in shoes, you can see that the data tries to pull this up to a detection, but in terms of the chi-squareds, it does not look favored. And effectively, you're just trading off, again, this S8 tension against the H0 tension.
3 minutes, Colin.
Okay, thanks.
Okay.
All right, we then proceeded to try to squeeze every drop of cosmological information that we could into this analysis by folding in results from this very nice effective field theory of large-scale structure that Misha Ivanov and others have applied to the BOSS data. So we combined his modified Boltzmann code with ours to build a super modified version of class. And these are the results that we got when we did this analysis. So now the EDE contours are shown in green or blue, where the blue folds in both Planck, BOSS, and then the S8 data from DES et al. And then the green does not have the S8 data. But if you look at folding in all 3 of these probes, you can see that the H0 value that we get, is pretty similar to what you get in lambda CDM. No major shift is seen. And there's still a very significant tension with shoes, even in the context of this expanded model. We get a pretty tight upper limit on how much of this early dark energy could have existed prior to recombination. Let me skip this. I think the interesting thing we've showed here is that the additional information from this EFT likelihood comes through the constraints that you get on the cold dark matter density from the shape of P of K, which is a nice application. And let me just mention quickly, there have been some claims that the results here are driven by prior volume effects. If you look in the appendices of this paper from last summer, we examined this in great detail and showed that, in fact, prior volume effects are quite small here. In the interests of time, I shouldn't go through this in detail, but let me just assert that whether or not you account for a frequentist approach or a Bayesian approach that could be sensitive to prior volume effects, you get effectively the same answer. Okay, so then in the last minute, I just want to briefly highlight that we have great data coming down the pipeline from ACT and Simon's Observatory. So the results that I showed you earlier from ACT were based just on our DR4 analysis that came out last summer, which included data through 2016. We've been collecting data in the intervening 4 years continuously, and we actually have 4 times as much data already on hand as what was released last summer. So our noise level is about 3 times better than Planck in our data that's on hand with arc-minute resolution. And if you propagate this to an H0 forecast in lambda CDM, we get an error bar of about 0.5 kilometer per second per megaparsec. So in the next, say, year or so, stay tuned for these very powerful results. And then what's coming up next in the Atacama Desert is the Simons Observatory, which is currently being built. We have a bunch of hardware down there already. And that will start observing in 2023, 2024, which will then decrease the noise level by another factor of 3 with multiple frequency channels, and thereby increase our sensitivity to not just H0, but all sorts of these new physics scenarios that I've discussed in the early universe. Okay, so let me just leave you with these main takeaways, and then I will stop here. Thanks.
Okay, thank you very much for this nice summary on the ACT physics. And so questions, please, or any comment?
Can I make a
Sure,
comment?
please, Levon.
Hi, Colin. Very nice talk. I
Thanks.
was very happy to see that you and your collaborators reproduced the results on clumping. That was really nice to see. So with Sylvia Galli and Karsten, we have analyzed ACT and SPT3G data in the context of the clumping model.
Mm-hmm.
And we find that SPT3G actually prefers more clumping, while for ACT we find what you did. So there is no controversy there. And then we tried to understand what makes ACT so constraining. And we traced it down to the normalization of the TE, part
right.
of, and which was also responsible for this little tensions with Planck. So I'll mention this in my talk a little bit, but my slides are also posted if you wanted to preview.
Okay, yeah, I'll be interested to take a look. It's true that, yes, there is a sort of few percent-ish amplitude that seems to be offset in the TE data from ACT. We spent a lot of time trying to investigate whether this could be due to some systematic that we don't know about. What's curious is that if it was a polarization efficiency systematic, you would expect to see something that goes like that value squared in EE, but we do not see any evidence of that. So it's at the moment unclear whether this is just a fluctuation or if it's something real, but we don't have any.
That was our take
hypothesis
too,
for it.
that it's not obvious why. There's no physical reason.
That's right.
for it. Yeah, it just seems to be that ACT is somewhat anomalously constraining on clumping. That's what we find.
I see. All right, I'll take a look at. I look forward to your talk later.
Okay, thank you.
Yeah.
Okay, I'm afraid we don't have more time for questions, maybe at the end. So I suggest to move to the next speaker. Manos Saridakis is he around? Yes, that's right.
Hi, everyone. Hi, Juan. How are you?
How are you? So please, you can share your screen or your presentation, and you can start as soon as you like on alleviating H0 and sigma 8 tensions with
Can you give me
FT gravity.
Can I share my screen, or because can you?
Yeah, please do it. Yeah, you can do it as soon as you like.
Because
you are not successful in doing it at the moment.
Let me see.
Now I can see. Yeah, please. You may
that
start.
That is a funny green framework. Anyway, so just I have 19 minutes, right? So just let me know 2-3 minutes before.
At 12 minutes, I will tell you, because it is 3 minutes before the end of your talk. Yes, sure.
Sure. But it's 19 minutes, right? The total time, or 15?
Yeah, the total. But I am talking about the top plus.
Sure. Very good.
So
Great.
at 12 minutes, I will tell you.
Okay. So first of all, I would like to thank you, Juan, for giving me the opportunity to give this talk here in this session. I apologize, I could not follow the whole session because I were giving talks to other sessions. So we are going to present a possible way to alleviate both H0 and sigma 8 tensions through torsional modifications of gravity. And actually, we are going to report on how we're going to do that. First, in a completely modeled independent way, and then in the framework of F of T gravity. And this is based in these research papers that we did. Now, of course, I will skip the introduction. In this session, you are all familiar with the H naught tension, that the value for the H naught that we indirectly estimate from Planck, assuming lambda CDM cosmology, is different from the local measurements of based on CFITs, and the sigma A tension, that there seems to be less clustering than the one predicted assuming lambda CDM cosmology. So, as you all know, when we have here in detail in this session, in order to solve the first tension, that's not tension, you can assume many frameworks, either at early or at late times, assuming, for instance, early dark energy or interacting dark energy with HERD or dark radiation, or improve Big Bang nucleosynthesis, or, of course, modifications of gravity. Now, for the sigma A tension, and again, this can be solved in various frameworks, assuming sterile neutrinos, running vacuum models, of course, as we hear, dark matter sector that clusters differently according to the scales, or again, by gravitational modifications. Of course, there are attempts that try to elevate both tensions at the same time. And of course, we heard some of them with interactions or dark matter neutrino couplings. And of course, since modifications of gravity can elevate both tensions, this is the way that we are going to follow in this talk, and choose a gravitational modification that can solve, at least alleviate the tensions. Now, in general, independently of the model, in order to solve the H naught tension, we need a positive correction to the Hubble function, so to the Friedmann equation at late times, in order to increase the value of the current Hubble function compared to lambda CDM. So this is the basic requirement. This is what we need. For the sigma 8 tension, of course, if we look on the equation that determines the clustering of matter at sub-horizon scales and during matter domination, usually takes that form. And here is, in general, the effective gravitational constant given by the generalized Poisson equation. So as you are all familiar with, in order to calculate the observable F sigma 8, which is the root mean square time-depending fluctuations of matter of a density inside spheres of radius 8 megaparsec, in order to be in the linear regime. So we solve this equation, and since we calculate delta, we defined F, and in the end of the day, we can calculate the sigma 8. Now, qualitatively, what does it mean that we have a problem with the sigma 8? It has to do with the fact that there seems to be less clustering than predicted. So how we are going to solve it qualitatively? Either we assume that gravity is weaker at intermediate scales, so quantitatively this effective Newton's constant should be smaller than the usual GR Newton's constant, and this friction term could play a role in determining the clustering, the matter of a density. So if we have an increased friction term, we are going to have less clustering. So in order to solve the first tension in a model independent way, we need the resulting Hubble function that is given as a correction comparing to lambda CDM Hubble function. And this is the phenomenological correction, this D of Z. So this is the correction, and what we want is the D of Z to be 0 at the CMB redshifts. So in order for lambda CDM at the CMB to remain unaffected, but we want this to play a role at late times and make H increase. Now, specifically, you can quantify this D of Z and take into account the phenomenological constraint. So, strictly speaking, we want it to be 0 during the CMB times and to be larger than 0, but always small in order for the deviations to play a role at late times. Now, for the second tension, we need a modification of gravity that has an effective Newton's constant less than the standard one. This can be both fulfilled in the framework of torsional modified gravity. And just very briefly, and to take it back home, in general relativity, Einstein's main crucial idea was that gravity is geometry, but geometry is quantified by curvature. So gravity is curvature. As Wheeler beautifully says in his book, matter tells space-time how to curve, and the curve space-time tells matter how to move. But later on, it was Einstein himself that found an equivalent way to describe gravity using torsion. Initially, his idea was curvature to describe gravity and torsion to describe electromagnetism. So using both curvature and torsion, so geometrical quantities, he could have a unification of gravitational and electromagnetic interactions. But in the end of the day, he found that torsion does not describe electromagnetism. Torsion is an equivalent way to describe gravity. And the idea is the following. Curvature and torsion are properties of the connections that you impose in your theory. And the connection is a concept completely independent from the metric. The metric comes from the Greek word to measure, so the metric on a space-time helps you to measure areas and distances and angles. The connection is related to the rule you impose in your theory in order to be able to parallelly transport your vectors. So for the same space-time, you can have infinite curvatures and torsions according to your choice of connection. In general relativity, we assume the Levi-Civita connection, which is the only connection that has zero torsion by contraction. Why? Because it is symmetric. However, there are other connections, and in this framework called teleparallel equivalent of general relativity, one imposes the Weinberg connection, which by construction has zero curvature and only torsion. So although in general relativity, gravity is geometry and geometry is curvature, so gravity is curvature, in torsional theories of gravity is still geometry, but geometry is torsion, so gravity is torsion. Now, a little bit more technically, in this kind of theories, we are using the tetrad fields, which are the orthonormal fields that form the basis on the tangent space. And the two tetrads are related to the metric, the usual coordinate metric or our manifold, through this expression. So these are the dynamical variables. And we impose the Weinberg connection instead of the Levi-Civita connection. So this by construction, it leads to zero curvature. And the difference of two connections, remember now the connection is not symmetric. So we define the torsion tensor in this way. So all the gravitational information is embedded in this torsion tensor. And in a similar way that in general relativity, gravity is embedded in the curvature tensor, the Riemann tensor, and by contractions of the Riemann tensor, you obtain the Ricci scalar, which is the Lagrangian of the theory. Here, by suitable contractions of the torsion tensor, we construct the torsion scalar, and this will be the Lagrangian of the theory. And if you take this Lagrangian and you perform variation in terms of the field binds, you obtain exactly the same equation with general relativity. That's why Einstein called this theory teleparallel equivalent of general relativity. Now, in a similar way that in curvature gravity, you can have models like Evovar gravity, so modifications of gravity based on the Einstein-Hilbert axiom. In torsion gravities, you can have torsional modified gravities starting from the teleparallel equivalent of general relativity. The crucial point that you need to remember and take back home is that although GR is completely equivalent with the teleparallel equivalent of GR. Their modifications in the naive way that we are doing in the literature, F of R and F of T, are different. I'm not saying that one of them is correct and the other one is wrong. All I'm saying is that this is a different classes of modifications of gravity. And if you go to F of T gravity, these are the Friedman equations, and you obtain an effective dark energy sector of torsional origin. So this is a different theory from F of R gravity. And the interesting feature is that the torsion scalar in FRW geometry is equal to 6h squared. So it depends only on the Hubble function, while the Ricci scalar in FRW is equal to Hubble square plus h dot. So it depends also on the derivative of the Hubble function. This will play an important role to our analysis. So we
3 minutes, Manos. 3
yes,
minutes.
yes, we consider the telepar equivalent of GR. This is just the cosmological constant expressed in terms of h naught and omega matter 0, and this is the correction. So this correction now will play a role at the background level. So it will, according to our discussion, it will solve the H0 tension, but also it will change the gravitational constant. So it will solve the sigma 8 tension. Remember, previously, we examined in a model independent way what should be the features of the correction in order to solve both tensions. Now, we impose a general F of T modification, and assuming that our model must coincide with lambda CDM during the CMB time and solve the tensions today, we numerically reconstruct the necessary F of T model. So these models that are numerically reconstructed can solve both tensions. And here you can see this is F of T. So this is the exact function, these functions. And here is the behavior of the Newton's constant. So here is the result. If you take these models, we can solve both tensions, at least alleviate both tensions at the same time. This is the Hubble function evolution. So this is the solution of the H naught. You see lambda CDM goes like that. Our models solve the H0 tension. So we have imposed coincidence at the CMB times, and later on, modifications of gravity solve the tension. And again, for the sigma 8, our models, because corresponds to weaker gravity, gives us less clustering, so alleviation of the second tension. And here is the distance modulus and the residuals, just to check that the proposed model alleviates both tensions. So, of course, this was completely numerically reconstructed, but now we can reverse things and we can propose this model. So this is just general relativity, cosmological constant, plus a torsional correction. This correction is adequate to change the background evolution and solve the H naught tension, and also solve the sigma 8 tension because it leads to less clustering. And of course, you can use data to confront these models from strong lensing at galaxy scales, of course, the usual data and gravitational waves experiments. So, in summary, we reported and we presented a torsional modified gravity model that can solve both H naught and sigma 8 tension. And this is just a correction and torsional correction to lambda CDM. So in a model independent way, first we understood what we need, and we need a modification that during the CMB times is 0 and plays a role at later times. And we were able to reconstruct it in F of T gravity. And of course, one could do the same, play the same game in different torsional modified gravities in other theories. So I finish here, and just to make an announcement, since Nick Mavromatis is also in the audience, we are organized as a cost on quantum gravity phenomenology, a conference and a school in Corfu Island this September. So you are all welcome to register and physically come. So thank you very much.
Thank you very much, Manos. Is there any question to this interesting talk? I certainly have a comment if there is no comments.
Joan, I think.
Oh, yes, yes,
Nico,
sure.
There are several, I think. I don't know
Yes,
who's first.
I couldn't see them before. Okay, so
Yeah, I don't know
please,
who's first.
I think
I
Levon
cannot
or
say.
Nico.
Okay, so please, I don't know. I mean, Nick, you can
Okay.
start.
A quick.
Let us
nice,
try to be short, please.
Yeah. Nice talk, Manos. Inflation in your model. How do you get it? You need the extra inflaton fields or through some non-linearities of the torsion?
Yeah, good question. You can do both. Either
try to be short, Manos, too,
you can
because there
either
are some
have
questions. So please.
a scalar field
Go
that
on.
plays the role, or you can use torsion to give you inflation. In the second case, you need to be careful because then the couplings and the length scale should be different in inflation at late time. So that could be a problem. But in general, yes, you can have both ways.
Thank you.
Okay, the next was Levon, but right? Or
No,
I
it's
cannot see
okay.
his
It
head.
was from the previous time.
Okay, okay. So Adria, I think, has a question.
Yes, I have one question. So thanks, Manos, for your nice presentation. If you take the value of alpha and beta that are needed to fit correctly the cosmological data, and then you apply this model at local scales, for instance, here in the solar system, do you reproduce the classical results which are found in GR?
Yes, because our model is just a modification of lambda CDM, not just of GR. So we have the freedom to play with extra parameters, and we can obtain completely lambda CDM. So we just deviate a little bit at late times in order to solve the tensions. Actually, we reconstruct it that way.
Okay, but I mean, you can reproduce the perihelion shift, for instance, of Mercury?
Yes, of course. No, at this kind of scales, it's completely equivalent with general relativity.
Okay.
Yes, it has been done by Einstein.
Yeah, thanks.
Okay, just a small comment, Manos. It was very interesting. I just want to tell you, if in case that you don't know, I mean, the kind of approach that you do, which is completely different from the one we used, is it is tantamount to doing the same. I mean, to change the strength of the interaction also for the gravitational constant, so on and so forth. This is exactly what type 2 running vacuum model does. So in fact, since, for example, your torsion scalar T is -6 times h squared, for example, exactly. Right? So you can just adapt very easily your model such that you could reproduce this kind of type 2 running vacuum model results that we find. So the strategy is essentially the same. And in this sense, well, I'm happy to see that from different perspectives, one can resolve the two tensions at a time, because the kind of prediction that you got for H0 at the level of 71 and even beyond, and reducing sigma 8 appropriately is also very similar to the one we found ourselves. Okay, so I can send you the reference in case that you ignore it. But,
no, I have the reference.
But you probably know.
Yeah, of course, we know very well. And we were actually thinking that probably this could be, that torsion models could be the missing Lagrangian description of running vacuum. But you know, the $1 million question, how to find an axiom for. But anyway,
well, we included in the stringy version of RVM, we have both gravity and torsion, as I spoke yesterday, as you know very well. So
exactly.
The only problem is that, of course, we have gravity because we only have the totally antisymmetric torsion, and it comes from string theory. But and that's why the quantum gravity corrections give the corrections that Joan give an RVM type vacuum because of the logarithmic H corrections. So it's
okay. Now, this is very interesting, of course, but I have to cut at this point. If there is time at the end, we come back to it, okay? Thank you very much, Manos.
Thank you very much.
So the next talk would be will be by Laura Salvati, please.
Yes.
It's you. Okay, thanks a lot. So yeah, you were here before and you checked, so please now, yeah, very good.
Okay.
So you can start as soon as you like.
Okay, so thank you. Hi, everyone. I'm Laura Salvati. I am a researcher at EIS in Paris. And today I would like to discuss with you what is the impact of the mass calibration in cluster cosmology and how it impacts the tension that we have on the sigma-8 parameters. So I will go very briefly through how we can obtain cosmological information from galaxy clusters, focusing on clusters detected in the millimeter wavelength. And then I will discuss some results that we have obtained in these two papers here. So we know that when we discuss about galaxy clusters, we are dealing with the very latest part of the evolution of the universe. And these objects are the largest structures that are gravitationally bound in the universe, and they represent the peaks in the cosmic web of the large-scale structure, as you can see from these blue points here. So they show a strong dependence on some cosmological parameters, and in particular on the parameters that describe the matter content and distribution in the latest universe, so the sigma-8 and omega-n parameters. And one of the very important characteristics of galaxy clusters is the fact that this object can provide observables along the entire electromagnetic spectrum. So it's really important to have a multi-wavelength analysis for a cosmological analysis of galaxy clusters. So when we are doing cosmology with galaxy clusters, we actually need to know their mass and redshift distribution. But in practice, the most used observables for cluster cosmology is the number counts. So it's really the number of objects in bit of redshift and the given observable that depends on the wavelength that you are considering. And when we model the number counts, we have these three key ingredients entering into the analysis. So the first one is the mass function, that is basically the theoretical mass and redshift distribution of clusters. And of course, it is related to the cosmological model that we are assuming. Then we have in pink here the selection function, that is basically how we model the detection and observational approach of the survey that we are considering, so our experiment. And finally, the ingredients that I will focus for the rest of my talk are the scaling relations between the survey observable and the cluster mass. And this is because we are never able to measure directly the mass of the cluster. For example, here you have the images for the coma cluster in the millimeter and X-ray wavelength. And in these cases, we are targeting the hot gas. While if we observe the clusters, for example, in optical or near infrared wavelength, we are actually detecting galaxies. So we need to relate these quantities to the cluster mass. And this is done through the scaling relations. And of course, this scaling relation basically represents the interplay between astrophysics and cosmology in the formation and evolution of large-scale structure. And given these three components, we need to model them as best as we can in order to reduce any possible source of systematics in the cosmological analysis of galaxy clusters. So I will focus on the analysis of clusters detected by the Planck satellites, so with the Tse effect. And just to remember, this is the inverse Compton scattering between the photons of the CMB and the electrons in the hot gas of the clusters. And this kind of effect basically leaves a unique distortion in the CMB frequency spectrum, so it's very peculiar to detect. And the observable is, in practice, this Compton parameter here. This is the integral of the pressure profile. So basically, it provides a good estimate of the total thermal energy of the cluster gas. And so it's a very good mass proxy. So this is the thing that we need to relate to the cluster mass to do cosmology. So in general, how do we build the scaling relation for clusters detected with the Tse effect? So the theoretical model is based on some assumptions. First of all, we assume self-similarity. So basically, gravity is the only force that is driving the collapse of clusters. Then we assume, of course, a spherical symmetry, and we assume hydrostatic equilibrium. So basically, we can provide this kind of relation between the integrated Compton parameter and the cluster mass. Now, if we go in details on what has been done inside the Planck collaboration, this is the actual scaling relation between the Y500 and M500. 500, it means that we are considering clusters as objects inside a radius that contain 500 times the critical densities. So we need to calibrate the scaling relation for the cosmological analysis. And now in practice, calibrate means obtain constraints on this parameter here. So beta, Y star, alpha, and 1 minus B. And as I was mentioning before, the best approach to calibrate the scaling relation is to use a multi-wavelength analysis. And so in particular, for the Planck analysis, what we did was to use X-rays observation to constraints alpha and Y star, and weak lensing observation to constraints 1 minus B. And then we assume self-similarity. Now, the first thing that we need to stress is the fact that the Planck collaboration provided like almost 2,000 clusters detected in the sky. For the cosmological analysis, we restricted this to 439 clusters with the highest signal to noise, and this is their mass and redshift distribution. Now, the problem is that to calibrate the scaling relation, we actually consider very small subsample of these full 400 clusters here. So as you can see, for the X-rays observations, we consider just 71 clusters in this mass and redshift range, while for the weak lensing analysis, we consider just 20 clusters here. So one of the first questions that we have to ask is if these subsamples are really representative of the entire cluster sample that we are considering. So now focusing on the results and on how the calibration of the scaling relations impact cosmology. So these are the 2D constraints for omega m and sigma 8. And these three curves here are all obtained from the same Planck cluster catalogs, just considering three different mass calibration. So if we focus on this 1 minus B quantity here, now this is basically the mass bias. So the idea is that we can evaluate the mass from TSE observations, but this is done assuming hydrostatic equilibrium. And we know that this is quite a strong assumption. Clusters are not fully relaxed, especially if we go to higher redshift. So to take into account mainly this departure from hydrostatic equilibrium, but also other possible effects, we introduce this mass bias as the ratio between the mass assumed as assuming hydrostatic equilibrium and the real cluster mass. So from hydrodynamical simulation, we have quite a strong evaluation of this quantity that is around 0.8, basically. Now, these three results here are obtained for different values of 1 minus B. The baseline was the results in blue, is from the Canadian Cluster Comparison Project analysis. And as you can see, this 1 minus B is basically around 0.8. But if you shift 1 minus B towards the lower value, you go up. And indeed, the very low value of 1 minus B, so around 0.6, was advocated as one of the possibilities to solve the tension that we had in 2015 between Planck clusters and Planck CMB primary anisotropy. So as you remember, we had like a 2.4 sigma tension on the sigma 8 parameter. The problem is that having such a low value of the mass bias is really not in agreement with hydrodynamical simulations and most of the weak lensing analysis. So this is our starting point. Basically, we wanted to improve the analysis of Planck TSE observations to further understand the calibration of the scaling relation and the impact on the tension with the CMB. So the idea is that we used the TSE number counts for Planck, but we also considered the full Y signal that we have in the sky. So we consider the power spectrum of the total Y signal. And it is because also in building the model for the TSE power spectrum, we have the same ingredients as the number counts. And in particular, we have the impact of the scaling relation. So ideally, combining the two probes, we should be able to break the generalities between cosmological and scaling relation parameters. But now, before moving on, we have to stress the fact that the Planck cluster analysis stopped at 2015, but the CMB analysis has been largely improved in the subsequent releases up to 2018, basically. And one of the main results, at least that interests us for this presentation, is the fact that we obtain a very lower value of the optical depth tau, and it basically drags down sigma 8. So if we now just focus on the constraints on cosmology from Planck cluster counts and Planck CMB primary anisotropies, we are fully in agreement with 2 sigma. We do not have a tension anymore on the sigma 8 parameter mainly. Now, at this point, we focus on the omega m and sigma 8 for the two different TSZ probes. So as you can see here, we have number counts in orange and TSZ power spectrum in gray. And you see that the two different probes actually show different dependencies on cosmological and scaling relation parameters, so the mass bias again. The problem is that with this level of precision and accuracy for the TSZ power spectrum, number count is basically mainly driving the constraining power, at least for the standard model of cosmology. Now, the problem is that even if we say we do not have a tension on sigma 8 anymore, what happens if we focus again on the constraint on a mass bias? So basically, if we consider again the combination of CMB primary isotopies with TSZ probes, as you can see from the results here, basically, the constraints are still around 0.6. And we also explore some extension to the standard model of cosmology just to check that it was not a hint for some new physics. So in particular, we consider the impact of massive neutrinos or the impact of the dark energy equational state varying with redshift, basically. But anyway, the results are still in agreement with 0.6, basically. And this were also confirmed in the 2018 analysis from Planck. But so the problem now is, it's just that like the tension from sigma 8 moved on the mass bias. So how we can understand this? And this is also in the light of the fact that 1 minus b around 0.6 is not only in disagreement with hydrodynamical simulations and different with lensing analysis. Here you have a collection of these. But if we consider also other astrophysical observables related to clusters, this value is way too low. So here you have an example of the gas fraction that you have in clusters. This is results from the XCOP project. They are analyzing 12 local clusters. And of course, the gas fraction can be related to the mass bias because it's anyway a ratio between the gas content and the total mass that we have inside the clusters. Now, this quantity is quite well understood and such that from hydrodynamical simulation, we can have a prediction of like a universal value. And this is what you can see here in pink. So basically fixing a value for the mass bias, we can provide an evaluation of the gas fraction. And this is exactly what they do here. And the green points are obtained for a value of the mass bias that is around 0.6. So this was the 0.58 from the 2015 Planck release. And as you can see, we are completely off with respect to the universal value. So this is even another tension, another a fact that the 0.6 value preferred from CMB is really not in agreement with
3 minutes, Laura.
Yes, observations that describe clusters. So at this point, one of the possibilities is to try to better characterize the mass bias. So coming back to what we have seen at the beginning, the fact that we are using a very small subsamples of clusters with respect to the full Planck cluster sample. So maybe assuming this constant value for the bias to calibrate 400 clusters is not the best choice. And so we try for a mass and redshift evolution for the mass bias, basically. And this is like really a simple parameterization. And we have to discuss two things. So first of all, if we combine again with CMB, like if we come back here very briefly, as you can see, the constraining power of CMB is way higher with respect to number counts, at least with current results. So they are, of course, driving the results, but this is really not giving us an info from a physical point of view on the mass bias. It's just like it's driving the results of the MCMC analysis, basically. But if we focus on the TSZ probes, we see that we find a hint of a redshift evolution for the mass bias. So if you see the green and blue lines here for the total mass bias with respect to redshift, this is increasing towards high redshift, but this is counterintuitive. We would expect 1 minus b to be closer to 1 at redshift 0, because it would mean that the clusters are more relaxed. And this is exactly what we expect. So we would expect an opposite trend. And we perform different checks in order to understand these results. And the most important one is related to how we select the sample that we are considering. And in particular, we decided to cut the low redshift part of the Planck cluster sample and redo the same analysis. And in this case, as you can see, so focusing here in the blue and red curve, we have exactly the opposite trend. So really changing the samples that we are considering for the full cluster sample is changing our results. But so it really means that we have to be careful in how we choose the mass calibration and the total calibration of the scaling relation in general, given that it can change the results so much depending on the subsample that we are considering. So having this in mind, I think I can directly go to the conclusion, and I hope I have stressed enough for you the fact that the mass calibration is really the largest source of uncertainties that we have, at least in current cluster cosmology. I've shown you results for Planck and how different choice for the mass calibration can shift the constraints, but the same analysis has been developed also, for example, for the South Pole Telescope analysis, and a similar discussion, you can find it also in the recent DES papers. Now, of course, we expect to have in the present and in the near future lots of other observations for clusters in different wavelengths. So it's really an exciting era for cluster cosmology, but we know that we really need to improve this mass calibration. And one of the points is to improve the theoretical modeling. So maybe move on from all these assumptions that we are doing of self-similarity and hydrostatic equilibrium, and try to really model better the interplay between astrophysics and cosmology in the cluster evolution. And we need, of course, a tight relation, let's see, between simulations and what we observe, and a multi-wavelength analysis of larger cluster samples. And only once we have done this, we can really check if there is still room for tensions between, in this case, clusters and CMB primary anisotropies, and see if we really have hint for new physics. And I think I can conclude here. I hope I was on time, so thank you for your attention.
Yeah, more or less, it is fine. Yeah, thank you very much for your talk. So, any question? I think. Easy. Nick, you
yes,
want?
can I?
Yeah, you can. I cannot see your hand, but I can see your eyes.
I can see your eyes. Very nice presentation and very good results.
Thank you.
Can I ask about since you mentioned the mass uncertainty and other uncertainties, what do you think about the uncertainties in dust models? Are they going to contribute to alleviation of tension? The uncertainty that we have since we don't understand the model of dust as well. What do you think?
So you've asked these questions a lot in this
yes,
session.
Because I know, because I still believe, according to recent things, that there is a big uncertainty there, and but I don't know. I want to see all the answers from the experts.
Okay, so I have to admit that I'm not really sure about how much it could impact on the results that we have up to now, especially given that, as we have seen, we are dominated by other sources of uncertainties that are impacting way much. I think that maybe at the level of the detection of clusters, I would say that dust is not the first contaminant that it comes into my mind. But yeah, that is my answer. But
no, it's fine. That's what I asked you. I just want to collect all the experts' answers on this. So it might be at the end you say when you reduce the other uncertainties. That's what exactly. I got from your answer. Thank you.
Thank you.
Any other question? We still have time. Actually, this issue of dust, I mean, Nick, I'm not sure that I understand your question. It is about treating dust with some different equation of a state than just zero pressure.
There are papers recently, as far as I know. I mean, we don't have time now, but I can discuss, which point out that the model for dust that we have, because they are using an earlier model of dust, and it could contribute, it could contaminate some of the results. So it's not the equation of state mainly, it's just models of the way they do the dust. I will try to send you some models.
So about this,
there are some papers. So it's essentially details of dust, but as also our speaker said today,
but not changing the equation of a state.
No. It's really dust, but details.
Okay.
Of course, dust players will know a crucial role in the BICEP results, right? They thought they observed, well, that's a different level. I will try to send you, Joan, some papers. I mean, it's one of the uncertainties.
All right. I'm curious.
But I agree,
So-
the mass, for instance, the mass uncertainty is a crucial one. So at the end, they may or may not be tensions. I mean, I hope there are tensions. I mean, personally, I would really hope that that's a hint for new physics. But you never know. I mean,
yeah, we have to wait and
We have to wait,
have more results, and then we will be able to really state something.
absolutely,
about it.
that is the perfect
Yeah.
statement. That
Exactly. Okay, so very nice talk.
Okay, thank you.
Yeah, thank you to you. So we move to the next, which is by George Alestas about the tale of the 8-0 crisis. George, yes.
Hello,
You,
let me
you are
share my
here.
screen.
Yeah, please do it. Okay. Yeah.
So can you see, because my something froze. Okay,
Yeah.
you can see, right?
Not yet in my case. Can you pass, I mean, show more pages? I don't know the other people, I cannot see. Yeah.
I cannot.
Now, very good. So please,
You can see now.
Yes, now. We can,
For some
well,
reason, my
no, now I see black.
not now. Before,
Well,
yes. not
Before,
now.
yes. Now I see black.
Now we see
yeah.
just a vacuum.
Yeah, something did not agree with my laptop.
Or empty space,
The-
whatever you want to call it. Now,
Well,
now
the
again.
very good.
Dark
you can
energy,
see,
yeah.
okay. I'm afraid
Yeah.
to full screen it now, so I will keep it this way.
Okay, go on, please. Now it's okay.
So I'm a PhD student at the University of Ioannina under the supervision of Professor Perivoularopoulos. My talk will be based upon three recent papers that we published with my collaborators from our group, and it will be titled "The Tale of A-Zero Crisis and the Gravitational Transition." First of all, as a small overview, we will start with a general introduction to the A-Zero crisis. Secondly, we will propose a late-time WM transition model as a solution. Thirdly, we will provide some hints of observational evidence for such a gravitational transition, and we will end by providing a summary and conclusions. Now, regarding the A-Zero crisis, I won't bother with that, you know, it's better than I do. So I will skip it. I will skip the first slide, and let me just say that the 8-0 crisis might not be such an accurate term for describing this tension. The truth is that this tension has very little to do with H0 itself, and the main culprit for it is the supernova absolute peak magnitude. And that is because the H0 value that's given by the SUS distance ladder measurement is calculated indirectly by considering an inferred value of the MB from the Cepheid period luminosity relation. And the main problem with this is that this value of MB was calculated for a redshift range of 0.023 to 0.15. Therefore, the H0 value at the present, which one gets from this method, is a product of extrapolation. We will take advantage of that and the fact that this methodology is oblivious to any change below Z equal to 0.023. Now, there are some do's and don'ts regarding the solution of this tension. One goes about resolving it. And the first one is to consider all the robust available data. The second one is to try and ease the growth tension as well. And if you should never use a local H0 prior, and if you have to use a prior, you should make it an M prior instead. Now, there are two schools of thought regarding this tension. The first one is that the problem stems from systematic errors in the SUS calculations. An example, a recent paper which considers the Cepheid luminosity calibration systematics. And the second school of thought is that this tension is a gateway to new and exciting late and or early time physics. Now, we will take the second, and in my opinion, the most interesting path, and specifically, we will consider a late-time solution to this tension in the form of a parameterization with dark energy transition at very low redshifts, below 0.023, coupled with a gravitational transition of about 10%. Now, the motivation behind our study is that it seems quite clear that new late-time physics are needed in order to resolve the tension. And due to the nature of the problem, a simple dark energy transition, even though it allows H0 to approach the value reported by SUSE, fails to solve the problem by itself. Therefore, another type of modification is needed, gravitational transition, which will in turn allow for transition in M, which, as we said, lies at the heart of the issue. We will aim to address two questions. The first one is whether this proposed model is able to provide a satisfying resolution to the Hubble crisis without worsening the growth tension, and whether are there any observational evidence for such parameterization. Now, to define our model, we propose a parameterization which contains a transition to supernova absolute magnitude, accompanied by a transition of the equation dark energy of state parameter W of Z, and we call this model the LWMPT. The model itself is defined by equations 3 and 4, which display the transitions of W of Z and transitions of the absolute magnitude with the help of a Heaviside step function, where MC is the supernova absolute magnitude as it is calibrated by Tse Effect for redshift below 0.001. And we have two parameters to be fit by the data, delta M and delta W. Now, the evolution of the dark energy density is given by equation 5, and the Hubble expansion rate takes the form of the two equations, with equation 6 split in two by transition redshift ZT. We impose two conditions on the ensembles. The first thing is that it should reproduce the comovable distance corresponding to the Planck-Lambda CDM for Z larger than ZT, as it's shown in equation 7. And the second one is that it should reproduce the local measurements of the Hubble parameter as it's shown in the relation 8. Now, the first condition fixes the parameters omega m, omega r, and h to their Planck-Lambda CDM tested values, while the second condition lists the relation 9 between delta W and ZT, where we have fixed the h at the HCB value and omega m at omega m times h square at 0.143 for consistency within this bench of the spectrum. Now, if we compare the form of the commutative distances predicted in the context of the LWMPT model, which is shown as the green and blue lines, without the proposed edge of Z deformations for the resolution of the Hubble tension, we see that this model is the closest to the Lambda CDM, Planck-Lambda CDM fit, while at the same time predicting a Hubble parameter equal to its locally measured value. And now, in order to fit the LWMPT to cosmological data, we have used the following datasets: the Plankton dataset, a compilation of 9 power data points, the latest Planck-Lambda CDM CMB distance prior data, and the compilation of 41 cosmic chronometer data points. Now, defining the chi-square as equation 10, the total chi-square as equation 10, and calculating the residual delta chi-square with respect to the Lambda CDM model for the LWMPT model as a function of ZT, and for WCDM with a value of minus 1.22 and omega m 0.143 that claim to solve the zero tension. We see that the LWMPT model provides a far better fit for low Z. Now, assuming now the main characteristic of the LWMPT model, as I said, is the transition in M, which can be connected with a gravitational transition through the relation 11, which comes up by the fact that the absolute luminosity of the supernova is proportional to the inter-second mass. And therefore, the form of the transition in M that is necessary can be seen at the left plot, where we have the Pantheon data, and we see that the transition in M at very low redshift is necessary to give the MC that is corresponding to the Cepheids. This transition can also be seen at the right plot in gravitational terms. And now we also present the best fit of the absolute magnitude, which are the blue points for various ZT for the LWMPT model, and the dashed line corresponds to the fixed MC value. Now, regarding the growth tension, we have used a generic CPL model that attempts to solve seemingly the H0 tension to demonstrate that all the parameterizations that use the late time smooth deformations of the Hubble expansion rate H set for Planck lambda STM are unable to resolve and address the growth tension. In the case of the CPL model, this is shown by these contours, where we can see that for the growth and SIMB dataset, the tension remains for various values of the CPL parameters. However, in the case of the LWMPT model, we would expect that the growth tension would be improved, or at least not be adversely impacted, since it does not fall in the category of smooth H-set deformations. Now, for some observational evidence for such a gravitational transition, we have used an up-to-date compilation of galaxy data to examine the evolution of the baryonic Talley-Fisher relation, which is given by equation 12, which connects the total baryonic mass of the galaxy with its rotation velocity. And a tension in this evolution of the BTFR could be attributed to a gravitational transition. Since, as we can see in the equation 13, the 0.8b of the baryonic Talley-Fisher relation is proportional to the effective Newton's constant. Now we concerned ourselves with the logarithmic form of the BTFR, which is a simple linear expression, as we can see in equation 14. And as I said, we can see that the intercept of this line is connected with the strength of the gravitational interactions. Studies of the evolution of the BTFR have been done in the past, but none of them has focused at searching for abrupt transitions of the intercept or slope values at very low redshifts. Now, and that's exactly what we did. So we considered the BTFR dataset of the updated Spark database, consisting of the distance, the logarithm of the baryonic mass MB, and the logarithm of the asymptotically flat rotation velocity of 118 galaxies, along with their 1 sigma errors. And the main characteristics of our study is that we have used an exclusively low Z sample of data. We have focused on a particular type of evolution, which are
3 minutes, George. 3 minutes,
thank
George.
Intercept, yes, of the intercept slope. And in order to find this type of transitions, we have used an analysis where we have fixed critical distance and split our sample in 2 subsamples below this critical distance and above this critical distance. And for each subsample, we have used the maximum likelihood method and performed a linear fit to the data while fitting for the slope and intercept parameters. Therefore, we tried to minimize this relation 15 with respect to slope and the intercept. Plotting now the sigma distance between each pair of subsamples as a function of the split distance, we observe 2 statistically significant abrupt peaks at 9 megaparsec and 17 megaparsec, which are close to what we expected, to what we wanted to actually find. So to summarize, we have stated that the true problem we have stated what the true problem is, which lies at the heart of the Hubble tension, and that it concerns the absolute magnitude. we have demonstrated how, at least in principle, a late-time transition model could provide the resolution of the Hubble crisis. This model is a phenomenological one and constitutes of a transition of the dark energy equation of state W, coupled with a gravitational transition, which is translated to an absolute magnitude time transition. And we have also given some observational evidence, hints of observational evidence, supporting such a gravitational transition in the form of a tension and the evolution of the PTFR relation. Looking ahead, in my opinion, the source measurement must be put under intense scrutiny in case of systematic error, which is a huge question that eludes so far. And the LWMPT model as well must be put under test using the full blind likelihood data, not just the CMB6 parameters that we already did, and be compared with other parameterizations that make similar claims. This work is currently underway, and we have some very promising results. Not so much for the transition in dark energy as for the transition in the absolute magnitude. And we could also consider some other statistical relations that involve gravitational physics, such as the Faber-Jackson relation between the intrinsic luminosity and the velocity dispersion of elliptical galaxies, or the Seyfert star period luminosity relation for similar type of transitions as in the case of the PTFR. So thank you.
Thank you very much, George, just in time. So if there are questions, we have time for a couple of questions.
May I ask a quick question?
Yeah, sure. Go on.
So a very good talk, George. My question is, okay, apart from the requirements, the kinematical requirements, have you considered any particular dynamical model that could be the cause of this gravitational transition? For instance, I remember that Leandros was telling me that if you want to enforce these requirements to F(r) gravity, then you get into the unstable regions of F(r) gravity. So F(r) gravity could not satisfy them. So have you had in mind particular model?
This is one of the plans. This is one of the things we want to do next. We don't have currently something in mind. We have considered FOPAR, but as Mr. Pervolaropoulos said, this didn't go far. This is one of the next projects. We don't have anything right now.
Very good, very good. Just remember that there is a F of T gravity. That's it. Okay, thank you, thank you.
Yeah, okay. Thank you.
More questions? Actually, why do you need two transitions? I mean, in particular, this transition for the absolute magnitude is a little bit surprising to me. I mean, what would be the physics behind this?
Actually, right now we're trying to constrain the model with more data, and surprisingly, the absolute magnitude transition seems to be the only transition that is needed to resolve the H0 problem. The thought behind it is that, as I said, in our opinion, the heart of the problem of the H0 is the absolute magnitude. It is mostly an M crisis, not an H crisis. So we try to resolve this tension by allowing for a transition in M. Surprisingly, from the data, the W transition is not preferred. So we're considering of, you could say, dumping the W transition. It leads nowhere. It's something extra. So if we were to keep one transition, it would be the M transition.
Yeah, but if this M transition is used, I mean, as the only clue to the H0 crisis, does this help for the sigma 8 crisis as well?
Yes.
Did you check?
Yes. I think my supervisor has a paper on this. I will send it to you. It is with Valerio Mara. I will send it to you later, so you let's say. It is actually the only one required to help with the growth engine. So
right.
at this point,
I will be
the
happy to
doubling
read it.
transition. Yeah. Okay.
Okay, thank you very much, George. So the next speaker would be Lilia Williams. Lilia?
Yes, hi.
About measuring the Hubble constant from gravitational lensing. So can you share your presentation, please?
I will share my screen right now.
Yes, fine. So please go on.
Okay, yes.
We
hi.
can see. Yes, sure.
Yes, thank you for inviting me.
Thank you for accepting.
My talk will be a review of recent developments in the measuring of H0 from gravitational lensing. So the source of the idea, so to speak, came in 1964 from a Norwegian astronomer, Sjur Revstal. And the very basic idea is that H0 is a property of the global cosmology, and it has units of 1 over time. So since light travel spans cosmological distances, light travel time will depend on H0. And so there should be a way to extract H0 from gravitational lensing. And a bit more specifically, light travel time from the source, which I have on the right here in the diagram, through different geodesics, which we observe as images, is a sum of 2 contributions that one has to consider. One is the geometrical, and that is the light path is related basically to the angular position of the image in the sky with respect to the source, which is not observed. And the other component is gravitational, which is the integral of the Newtonian potential, since this is weak field limit, Newtonian potential along the line of sight. And this is also sometimes referred to as the Shapiro time delay. So to make it slightly more quantitative, I have now labeled in the diagram above right here, I have labeled the position of the source, which is beta, and all these are with respect to the optical axis, which is defined as connecting the observer and the center of the lens. So there's the position of the source and images I and J. So this arrival time can be written down as a combination of the 2 terms. So this is the geometrical term, which is basically the square of the separation on the sky between the image and the source, and the gravitational part, which is an integral over the observer sky, the lens, of the normalized surface mass density, which we call kappa in lensing, with the logarithmic kernel. So there's also a prefactor, which is the important part for us here, which consists of angular diameter distances, and each angular diameter distance, as you know, is a product of C over H0 and a function of cosmological parameters like omegas and maybe equation of state. So this is where H0 comes from. And there's also the redshift of the lens, but that is usually when we see the lens, it's very easy to know what that value is. So the geometrical and the gravitational part combined gives you the lens model prediction of the arrival time. And we sometimes call it tau, sometimes it's called, I'll just call it tau. So this arrival time is not observed, directly it is not observed. What is observed is the time delay between images I and J, any 2 images. And so it's delta t, and that can be then written as the delta in the lens mass model divided by H0. So delta t we observe, delta tau we build from our models, and H0 is what we derive. So that's the essence of the method. And this theory is very simple, very straightforward. Where all the trouble comes in is through the uncertainties, of course. And there are a number of uncertainties that one has to consider. So first, let me start with what I have here in the upper right of the slide. And that is the fact that the universe does not consist of just the source and the lens. There's also a whole bunch of mass distribution along the line of sight. It's going to be a minor contribution, but it is still a contribution. So one has to take into account if one wants a precise and accurate determination of H0. So luckily, it was recently determined that having these clumps along the line of sight does not introduce a bias to H0, but only a scatter of a couple of %. And that's for one lens. But all modern analyses use not just one lens, but a handful of lenses. And in that case, the uncertainty goes down to something quite manageable, and in fact, it can be neglected. So I'm not going to talk about that anymore. The observed time delays, the typical uncertainties range between 1 and 10%. Of course, if the uncertainty is larger than that, you're not going to use that time delay. So practically, it's somewhere in the few percent, and I'll come back to that briefly in the next slide. The cosmological parameters, as long as they are close to values which are derived by other observations and are consistent with all cosmological observations, then this uncertainty is small, and I won't talk about that either. The main source of uncertainty is the lens mass distribution in the lens plane. And there the uncertainties, depending on who you ask and how you count, can range from few percent to 10%, or maybe even larger. But let's be optimistic and say it's few percent, a lens that 10%. So that's what I'll mostly talk about, which is where the big red arrow is pointing to. But first, a slide on observed time delays, because this is also, it's interesting. So quasars vary in time, unpredictably. So you can measure how their flux varies as a function of time, and this is what I have here. You'll notice that the time scale goes from 2004 to 2018. So this is a big effort. And the main collaboration which is doing these type of observations is Cosmological out of EPFL. And it is a dedicated program. So for this particular lens, which I have here as an example, the 4 light curves are plotted here, and you can trace that this particular feature in the flux of the quasar arrives at different times. So this is how we can measure the time delay. So basically, simply speaking, you slide these light curves until you find a match, and that gives you the time delay. In practice, of course, that's done in a much more sophisticated way, using different algorithms. And I have results for just one time delay of typical measurement through these different ways of doing so. And the final result for this particular time delay is of 36 days, and it's about 2%. In general, like I said, 1 to 10% is what we have. So that's the time delays. Now for the mass models. And to start mass modeling, we first assemble our modeling constraints that we have from lensing observables. So quasar image positions, which are these 4 here, time delays, and these 2 are always used in any analysis that wants to derive H0. Then in principle, we also have fluxes of images, and what is actually observable is the flux ratios, because we don't know the intrinsic luminosity of the source. We don't see the source. But there are caveats that go with this, and that is that the flux ratios can be affected not just by the global mass distribution, which is what we need for H0, but also with very local effects in the lens, stars and lambda CDM subhalos. And these are not very useful. So usually flux ratios are either not used or used with caution when deriving H0. There's also the host galaxy of the quasar source is imaged into an Einstein ring. And in this particular case, you see it's very, very pronounced. However, in some cases, the signal to noise associated with this ring has pretty low signal to noise. And also the optical resolution, spatial resolution, sorry, is not very good compared to the image position, what we call astrometry, basically how well you can determine the positions. There's about a factor of 10 difference between this and that. So sometimes that is used, sometimes it's not. All of these are lensing observables, and so they're subject to lensing degeneracies. And the most famous of the lensing degeneracies is the so-called Nash sheet degeneracy. Now, this is an exact mathematical degeneracy, but what is actually a problem to lensing is not the exact version of it, but the approximate Nash sheet degeneracy. And that can be summarized by calling it a steepness degeneracy, because what it does, it changes, in effect, it changes how steep the mass distribution of the lens is. So here I started with this model, which is represented by black, and this is log density on the vertical axis. And then I can change the parameter which describes the MSD, and I can make it steeper, which is in pink, or less steep, which is in blue. And there's a corresponding stretching of the time delay surface, which we have here. Right, so basically, recalling the formula from below, if we stretch the surface, this arrival time surface, then H0 will be effectively muted. So how do we break this degeneracy? How do we know which one of these profiles is the correct one? So what one wants to do, and that was identified a long time ago, is that if you have an independent means of figuring out what the density is at the very center, then that would break the degeneracy. So specifically, if you use stellar kinematics, meaning you measure the velocity dispersion, and as you know, the velocity dispersion tells you how much mass there is. So if you do that, say, just at the very center, then that will tell you whether, if you have a lot of mass, then it's more like the steep density profiles that are relevant in this lens, or if you don't have too much mass, then it's the blue ones, and that will break the degeneracy. So that will be great, and it works kind of okay, but there are problems with that as well that have been identified. So there are assumptions that go with implementing kinematics to measure the central density, and these kinematic priors have a significant impact on the result. They can introduce a bias. And also, it was also realized that in some cases, unresolved kinematics, meaning measuring the mass, the amount of mass just at a kind of one cylinder going through the center of the lens, that has limited power to constrain the mass profiles. The good news here is that in the near future, JWST, James Webb Space Telescope, will give us resolved, so spatially resolved kinematics, meaning we're going to have the velocity dispersion not just in a single cylinder going through the center of the lens, but at multiple locations. And that has great hope in breaking mass degeneracy. Now, there are other degeneracies as well. So this is mass degeneracy that I talked about. There's also a generalization of mass degeneracy, which is called the source position transformation. There's monopole degeneracy. Again, its exact version, mathematically exact version, is not a problem for determination of H0, but approximate version can be a problem. And also there's a whole bag of shape degeneracies, which frankly speaking, we just don't understand very well. And they could be an issue. And I'll give you an example of shape degeneracies in a second, in a minute. Okay, so that was modeling constraints. Next, having sort of made an account of our modeling constraints, we can actually go ahead and build a model for the mass distribution of the lens. So since the list of modeling constraints was not very long, you can guess that the lensing data by itself, even with kinematics, is not sufficient to generate a unique lens model. So one needs to appeal to other assumptions, which come in the form of our prior knowledge about galaxies. And since when studying lensing, that's not the first time astronomers have encountered galaxies. We've been studying galaxies for a long time, so surely we have some prior knowledge that we can use to help us with this H0 determination problem through lensing. So there are many different ways to characterize models and how different groups of people build models. And one way of them is to count the number of modeling parameters that different models have. And this is what I have on this horizontal axis here. So these numbers are approximate. So on this end, on the left end, we have models that have the least number of parameters associated with them. And these are the types of models that Holy Cow, the most famous group which determines H0 from lensing, uses. So they use one mass component models and two mass component models. And for one mass component, So you have something like an elliptical power law with a variable slope. And maybe you have a tidal term, which in lensing is called shear, which basically accounts for the mass, which is affecting the lensing, but the mass itself is located somewhere far away. So you can include that, and that gives you, in the single digits number of parameters. You can have two mass components. One would represent the dark matter, and another one will represent baryons, stars meaning. You can also have a tidal term and maybe nearby galaxies, and so the number of parameters is somewhere in this region. You can introduce one more complication to the mass distribution. You can assume, unlike what Holy Cow does, is that the two components are actually not co-centered, but they're slightly misaligned. There's a shift between them. And what that does, it introduces non-elliptical perturbations to the mass distribution. And what's important is actually just looking at what that does in the annulus of the images, not at the very center. So that introduces another couple of parameters. Or you can completely abandoning representing distinct mass components with individual functional forms, and you can say, I'm going to pixelate my lens plane and basically have my mass distribution be represented by a free-form distribution. So each kind of vary on its own, but there are some global constraints that keep the total mass distribution looking like a galaxy as opposed to some jigsaw puzzle. Okay, so there are other considerations that go with the number of parameters that you have. So on the left hand, where you have priors.
So 3 minutes, please, Lilia.
Many, the degeneracies which are present in lensing would be eliminated by, some of them will be eliminated by the strict priors that you put. And in that case, the uncertainties could be overestimated. So this is kind of saying I have an optimistic view of the lensing situation because I think I'm pretty confident about my parameterization. On the other hand, you have fewer priors on the right-hand side. And so you allow a wider range of degenerate models and your uncertainties could be overestimated. And this represents kind of a more cautious attitude or approach to lens modeling. In my opinion, you need different types of modeling philosophies in order to constrain systematics. So let me give you an example of what, for one particular lens, what the mass distribution looks like. So this is from the Holy Cow. This is a one mass component. This is from this set, which actually they did not derive H naught. And this is a free-form distribution. Mass distributions look quite different. And in the next slide, I'll show you what they mean for H naught. So I'm going to present results for the parametric models and the free-form models. And this is what we have for results. So let me start with Holy Cow, actually, which is in the field of H naught derivation from lensing. This is the result that you've probably heard of. So the value is constrained at 2.4%, and it is in with the CMB, with the Planck measurement for sure. And that analysis uses 5 quads and 1 double. So about a year after the Holy Cow result appeared, the group revisited their modeling and they relaxed their assumptions, their modeling assumptions somewhat. So they dropped the strict constraints on the mass density profile, and instead they added kinematic data from a larger sample of galaxies. And I won't go into details, but basically that kept the value of H naught the same, but it increased the size of the error bars to account for systematics. If you also insist that there's some self-similarity between mass profiles of the galaxies, then the central value of H naught shifts a little bit and the error bar shrinks somewhat. And now this result is completely consistent with Planck. So this is what happens when you change how you treat your assumptions about the mass distribution. So these are parametric models. Now, I'm associated with this group, and I have the 3 papers that we published since 2006. We have increased the number of systems. So we started with 3 quads and a handful of doubles, but doubles are not very useful really in this. And we went to about 8 quads. And our error bars shrunk. The central value remained about the same. And we are also not in conflict with the Planck measure. So if we depending on
there's some background noises here.
Mano, can you mute, please? I think Mano is you. Can you mute, please?
Yeah, there's some background noises. Please mute all microphones. Hello? Please mute all microphones.
You can do it, Joan. You can mute everybody. Just say mute, except the speaker.
But
I can done anyway. So
sorry, Lilia.
Yeah,
Go
no
on,
problem.
please.
Right. So
You
depending
should
on whether you take
come to the end soon, please.
depending on whether you take this result or that result, there may or may not be tension with the CMB value. And the best check on systematics, and so the size of your error bars basically, is to use different modeling philosophies, and as I've shown here. And I'm not going to talk about this, but I'll just say that there are many exciting things coming in the future, results from cluster lensing on H0, and also new variable sources in addition to quasars. Thank you. Thanks for listening.
All right, thank you very much, Lilia. There is very few time, short time for one question, for example. Any question, please?
I have one question, Joan.
Yeah, please, Adria, go on.
Thanks a lot, Lilia, for this very nice presentation. I have one question. Do you think it's feasible to achieve the 1% precision in the next years using wave lensing observations?
That's a good question. As Wendy Friedman said yesterday, CMB set a very high bar at 1% precision. And personally, but this is just my opinion, not necessarily the whole lensing community, is that it would be very hard to achieve 1% accuracy and precision on H0 in the near future. When we have more, when LSST comes online and we have a lot more lenses, then it might be possible, but not in the next year or 2.
Okay, okay, thanks.
Thank you.
Very good. Any other question? Short, please. Okay. So thank you very much, Lilia, for this nice talk. So the next speaker is Levon Pogosian. Levon?
Hi, Joan. Joan,
So,
you can mute anyone yourself manually. Can you please mute?
But I
Emmanuel?
can see everyone muted now.
Okay, good.
That's the problem. I know that there is some background noise, but I don't know what is the origin because everybody is muted now.
It was Emmanuel. It was Manu.
So
okay.
yeah, but he knows now. So please go
Good.
on.
Okay, so I hope you can see my screen, and
We can
so I'll talk about some work I did with Karsten Adamczyk a year ago, and some more recent work, which is a paper in preparation which includes Sylvia Galli. And I'm sure you've seen this plot before. I want to kind of provide my take on this plot, which is that there is tension. And if you look at what the tension actually is, it's between measurements that involve using a model for calculating the sound horizon, like a model of recombination, and those that don't. So CMB certainly relies on a model of recombination, and BAO as well, because you need a model of recombination to calculate the standard ruler, the sound horizon at baryon decoupling. So what happens to the BAO if you don't use a model and treat this RD parameter as an independent variable, but you use other data to help BAO constrain parameters, but data that does not rely on recombination? For example, you could just put a prior on omega matter H squared, or you could use galaxy weak lensing or CMB lensing. And then you can see that the tension with BAO, between BAO and shoes, disappears. So if you look at these plots, BAO is quite happily in the middle between Planck and shoes. But of course, the sound horizon is smaller than what Planck would predict. So that suggests that models that reduce the sound horizon could offer a solution. And there was no shortage of models proposed that achieved that goal, but I would like to single out primordial magnetic fields for good reason that they were not invented to solve the Hubble tension. It's a very old subject, and all of the mechanics that I'll be describing has been developed before Hubble tension was a thing. So no new changes were introduced as a result of the Hubble tension. So as I mentioned, the problem of magnetic fields in the universe is a very old problem. And the problem is that we see magnetic fields in galaxies, clusters of galaxies, even in the intergalactic space. And the origin of it is not completely explained. There is always a possibility of astrophysical origin of these magnetic fields, but there is no clear explanation based on astrophysics. And because of that, primordial origin was also seriously and is seriously considered. And recently, there's been growing evidence for possible primordial origin of magnetic fields coming from observations of cosmic rays and these filaments seen by LOFA. So I'm not going to go through this in any greater detail. I refer you to a recent review by Tanmay Vachaspati. Now, how do magnetic fields help with the Hubble tension? Colin Hill in his talk already very nicely explained. Just to summarize, here we talk about stochastic inhomogeneous magnetic fields. So there would be inhomogeneities in magnetic energy density. And baryons would clump or congregate in regions of lower magnetic energy density. So that means you have inhomogeneities in baryons, and that speeds up recombination. Now, so in our model, that's the new ingredient. There is this additional clumping of baryons, and it's a model-dependent parameter, but we have one additional parameter called baryon clumping. So a year ago, Karsten and I wrote this paper where we shown that if you allow for such clumping, then you could significantly relieve the Hubble tension. And in this plot, you see a best fit from Planck combined with 3 independent determinations of the Hubble constant, one of them being shoes. You can see that the curves, there are 3 curves. One is the Planck lambda CDM, and then 2 models of clumping. So this shows that there is a model dependence, but it's not a fundamental model dependence, meaning with better MHD simulations, we will definitely be able to converge to an ultimate correct model. So it's a temporary model dependence. And also, you see that when you add shoes, you get to Planck, or get H0 measurements to Planck, CMB moves to the right. Without shoes or a prior on H0, Planck does not by itself prefer non-zero clumping, as you would also see from Colin's talk. But the best fit, the chi-square to Planck, doesn't get much worse. It's actually both give acceptable and very good fits. If you look at the probability to exceed number, PTE, for lambda CDM, Planck has something like 17%. And for this model that you see that gives you a relief of Hubble tension, it's 15%. So it's hardly a degradation of the fit. As a byproduct, this also relieves the S8 omega matter tension. And that's because the physical matter density, omega H squared, stays the same, but H gets larger. And so as a result, you relieve the tension. Now, if you combine Planck and let's say shoes and add BAO and supernovae, then you get this relief of tensions, but adding BAO prevents you from achieving higher values of H0. And there is a fundamental reason for it that applies to all models that attempt to solve the Hubble tension by reducing the sound horizon. And that's because this degeneracy between the sound horizon and the Hubble constant is along a different direction for CMB and BAO. So here we treat RD as an independent free parameter, and each line here is at a fixed omega meter h squared. So if you follow the CMB line, you achieve an agreement with shoes here, right? But BAO achieves an agreement with shoes here. So they're agreeing at a different place. So in order to achieve an agreement between all three, BAO, CMB, and shoes, you have to be at a higher meta density. And the higher meta density runs you in trouble with the S8 tension. So that's a very generic reason why you cannot fully resolve the Hubble tension with the sound horizon only. So what are the implications of this? So as I said, you can relieve the tension, you can achieve H0s up to maybe 70. Now, the amount of clumping that's required, that number B, corresponds to approximately 0.05 nanogauss in co-moving pre-recombination magnetic field strength. So that's a special number. If you look at all the available constraints on cosmological magnetic fields, so on the top, on a left axis, sorry, vertical axis, it's the magnetic field strength in co-moving units on a particular scale, and the x-axis is the scale. You see, there is this golden square, which is the kind of magnetic field strength that satisfies all the constraints and can naturally explain cluster and galactic magnetic fields. So if you translate that, what it implies for our value of B, it falls smack on that golden triangle. So needless to say, we were very excited about this. And whether or not this scenario solves the Hubble tension, it's still extremely interesting to investigate this. So this is a highly falsifiable proposal. It can be easily ruled out by future observations, and high resolution CMB data is going to play a very important role in this. In particular, this kind of clumping affects the amount of silk dumping, which affects the power of CMB at high L. And so that's why experiments like ACT, SPT3G, and future experiments will be very useful in constraining these models. So since our paper, some new data came about. There was new BAO data, and the shoes value shifted down a little bit, but neither significantly changes any of the conclusions. So notable new data came from ACT and SPT3G, and they provide higher L spectra, and ACT DR4 has TT, while SPT3G only has, ACT DR4 has TT, TE, and EE, while SPT3G only has TE and EE. So these are the new constraints. And on the left, I have constraints without putting a shoes prior. And on the right, I have constraints with shoes prior. Excuse me, I need to tell my dog to go away. Hold on a second. Dog, out. It's an annoying dog. Anyway.
I discount 10 seconds.
Okay.
Go on.
Okay, so you see that there is a stark difference between the impact that addition of SPT has on the constraints on ACT. So SPT actually prefers more clumping. So without shoes, you get this bump in the blue line in clumping, and correspondingly H0 is shifted to a higher value, while ACT is distinctly disliking clumping. So there is a clear shift to the left. With shoes, there is a detection of clumping in all cases, but the significance of detection changes from 3 sigma to 2 sigma, depending on whether you use SPT or ACT. So clearly, there is a strong constraint coming from ACT. So that's why we set out to investigate what is it about ACT that makes it so much more constraining. So if you look at the differences between the data, so ACT has band powers, CLs, out to 4,000, while SPT only has them until 3,000. So you could ask, is it that? The answer is no. You can cut that part of ACT and constraints stay exactly the same. You could also assume maybe it's TT because ACT has TT, but SPT does not. That's not it either. If you remove TT, actually constraints on B get weaker. So TT actually prefers clumping, while it's basically the TE that EE that is constraining. And we did some mock simulations based on lambda CDM prediction using all the parameters of ACT and SPT3G to check what constraints should be. And we found that basically ACT constraints are much tighter than you would expect them if the true nature model was lambda CDM. So, and this anomalously strong constraints come from the TE plus EE portion of ACT data.
3 minutes, Levan.
Yes,
3.
that's perfect. I'm almost finished. So we were able to trace this to this normalization of TE spectra, which is known from ACT papers. They themselves emphasized, but they observed that a 5% recalibration of the TE amplitude can help to resolve this 2 sigma-ish inconsistencies with Planck. So there is no apparent reason for doing so, but if we do, that brings ACT constraints in line with the expectation. So this is a plot showing what happens to ACT constraints when you either make this parameter free with some prior on this amplitude, or if you just fix it by increasing it by 5%. And so that's the difference between the blue line and the dotted and the dashed line. So either way, you significantly relax the constraint. Now I want to point you to this line here, which is ACT, the solid line here, which is ACT DR4 TEEE. You can see that how strong the constraint is and how much weaker it becomes when you do the shift. So also to show that the constraint from TEE is significantly stronger than the constraint from all of the ACT data. So there's clearly something anomalous happening here. When you add more data, you're expecting your constraints to get stronger, not weaker. So this brings me to my conclusions. As I said, Hubble tension hints that something is missing in the physics of recombination, because if you take that away, then the tension basically disappears. There is a limit to how much you can do with this model. H0 cannot go beyond 70, but the values you get from supernovae and other low redshift measurements keep shifting. If you watched Wendy Friedman's talk and others, there is an evolution there. So I wouldn't be surprised if the values settled at 70 or below. And again, I want to emphasize that even if there was no Hubble tension, and if magnetic fields did not solve it, it's still very interesting if you see any evidence of this clumping, because by itself, it offers this tantalizing evidence of some new physics that would solve a much older puzzle, which is the origin of magnetic fields in the universe. And we can look forward to future CMB experiments where this high resolution measurements of temperature and polarization and anisotropy will definitely provide a conclusive answer. So thank you very much.
Thank you, Levan. Just in time, except for those 10 seconds from your dog.
Yeah, it's happily chewing a bone now. Yeah.
Okay. Any question, please?
I just wanted to make one quick comment. So the change in ACT versus SPT, I mean, it only looks like about a 1 sigma difference, right? So it's not all that significant, really.
That's true.
I guess just one other general comment also. I mean, depending when one adds data, I mean, you could get a improvement in constraints or a weakening of constraints, right? It depends on what the central value preferred by the new data actually is. So it's not generically true.
So what is the needed strength of this magnetic field that you need in order to
So as I
problem?
mentioned, it's about 0.05 nanogauss.
0.05 nanogauss.
0.05 nanogauss, yeah. So it's below current constraints on primordial magnetic fields you get from other places. Quite significantly below. So this could be the only way to actually see them in the CMB.
Okay. But in fixing the value of H naught, what do you have to say about sigma 8? I mean, with this mechanism, what is your prediction for the other tension?
For which tension?
Sigma 8.
So here you solve the SI tension completely. It's just because
but it doesn't have any impact on the other on the companion tension.
Yes, I'll show you the plot here. So this is
okay.
Yeah. So in this model, you solve both tensions, but not. Yeah. I mean, the H naught tension doesn't. You could say it doesn't. It's not solved, but it's relieved. It shifts H naught in a higher direction, but at the same time it shifts S8 also in the right direction.
Okay. If there is no other question, then we move to the last speakers today and for this session, which is Giuseppe Fanizza on precision cosmology and Hubble tension in the era of LSS surveys. So please share your, yeah, that's right.
Okay, very good. So
first of all, go on, please.
Yes, thank you, the organizer for giving this slot, and also let me thank George Alestas for switching because we had this superposition. But so now I am the last one of the day, so I promise to not bother you so much. But in this talk, I want to just talk about these results that we got presented this preprint here with my former master thesis, Bartolomeo Fiorini, which is now his PhD in Portsmouth. And in particular, this is about estimating how large can be the cosmic variance due to relativistic effects in the forthcoming surveys regarding large-scale structure surveys. So just a brief recap about the status of the art, even if I think that it is not really necessary because it's been widely discussed during these sessions. So we know nowadays that there is this tension running between the estimation of H naught coming from CMB data, which are precise enough to be to allow us to make precision cosmology, but are still needing for an assumption of a cosmological model to fit the data. And the local measurement, as we can infer the value of H naught from the luminosity distance redshift relation, and in particular just by linearizing this background relation between the luminosity distance from a given source and the observed redshift measured by the same sources, we can have that just the linearization of it can provide us a way to, just by measuring the dependence of this relation, a way to estimate locally the value of H naught, which on the other end, is model independent because those two estimation of redshift and luminosity distance are independent. But it seems not to be precise enough to be competitive with the one obtained by CMB measurement, of course. So the status of arts nowadays has become very intense, and as we can see, we have a lot of estimation, not only from, let's say, supernovae local estimation in CMB, but in the very last few years, we got several independent probes about the estimation of H0 from, I mean, we also listened some very interesting talk, for instance, about time delay lensing during this session, and the situation seems to be there. There is this tension that we need to understand better whether there is a possible source to do some systematics, or there might actually be some new physics just behind the corner that we would be very happy, of course, in this regard. So just to tell you what I want to do here is I'm just working within lambda CDM models, and just by considering the role of inhomogeneities as encountered by light traveling from the sources towards us, I want to estimate whether, I mean, how large is the impact of those inhomogeneities in the estimation of H0, so in the precision of the estimation of H0, just by taking into account realistic forthcoming surveys which deal with both finite number of sources and finite sky coverage of the surveys itself. It has been shown from the theoretical viewpoint that for a single source measured from a single observed source, there is a variance which can be associated to a single data point in the estimation of the luminosity distance redshift relations, and these variants vary with redshift as shown in this plot here, and is basically dominated by two essential relativistic effects. On very small redshift, we can see that the variance is highly dominated by the presence of the Doppler motion of the sources with respect to our rest frame. On the other hand, on the contrary, when we move towards higher redshift, we have that the variance is dominated by lensing effect. So we have to keep in mind that those are the two important contamination from the theoretical viewpoint, which might alter, let's say, the estimation of H0 from local sources. Just by doing this estimation, this is the purely theoretical regarding one single measurement. But as I anticipated before, what we have in mind is to deal with realistic surveys, which might be achievable in the next decade. And in particular, as a reference working case, we can deal with this histogram, which is forecast about the expected distribution of superluminous supernova as might be achieved from the Euclid and LSST collaboration in this recent paper. And in particular, we can see that for both the surveys, Euclid and LSST, we have a sky coverage which can vary a lot among the adopted configuration. In particular, we have that the narrow line, the line of sight of Euclid deep surveys in the deep configuration is very narrow, and in particular, it's also covering two opposite regions in the sky, whereas the sky coverage assumed reliable by LSST is way larger and it's way larger than the one got claimed by EDS. So in this sense, that now the point that we want to understand here is how to connect the theoretical estimation about the counting of inhomogeneities in those surveys with the estimation of H0. And in this regard, we can I mean, we need to provide an estimators for the evaluation of H0, and in particular, I mean, the simplest things that we can think about is just by acting with let's say an actual average on all the number of points that we might have at our disposal, but acting this average on the let's say luminosity distance redshift relation after being inverted, in a sense that just by having in mind the background relation, we can invert the value of h. We can infer the value of h naught from the luminosity distance and express the inhomogeneities sourcing the measure source by source to h naught by the one inferred by the luminosity distance redshift relation here. And in principle, since this is a quadratic estimator, we have to take into account both linear and quadratic perturbations to properly take into account the leading order effect. However, when we want to apply this estimation to the variance of the value of h naught obtained by a finite number of sources catalog with partial scale coverage with respect to the, let's say, call it the bare value of h naught, we have that the only relevant quantity which survives after some simple algebra is just led by the presence of linear inhomogeneities are correlated on angular scales. So it means that the only things that we need from theoretical viewpoint to properly take into account this effect is having a good understanding of the two-point correlation function of luminosity, of the linear luminosity distance redshift relation. So this is the only effect that we want to we need to deal with, and in particular, it is well known that from the linear point of view, this luminosity distance redshift effect is sourced by 5 kind of relativistic effects, which are, for instance, lensing, Doppler, and then time delay, local and integrated Sachs-Wolf effect. But among all of them, not all of them takes the same role in the estimation, and in particular, as we have anticipated before, the only two which are the most important one to this analysis are due to lensing and peculiar velocity terms. And in particular, the things that I would like to show in these plots here is the two correlation point function, the two-point correlation function regarding only the lensing effect. As we can see here, here we have those data points which are just by, let's say, numerical integration, assuming linear power spectrum, and a multiple reconstruction of of the full analytical expression evaluated just by hand, truncated at few multiples, L equal 19. As we can see, if we are not so close to the configuration where the two sources are aligned, the situation is not dramatic, such that we can have that already, let's say, a truncated at L equal 20 reconstruction of the two-point correlation function from lensing might be enough to get rid of the wall effect. But in particular, the things that turns out to be interesting is that if we go higher and higher in the value of the mean redshift in the bin, we have that these functions here, even in the exact reconstruction of those data points, becomes a way more peaked as long as redshift becomes higher. So in this sense, we have that this angular two-point correlation function can be somehow seen as, let's say, a spike function when the sources are are really aligned, and this function becomes rapidly negligible in value. So for the purpose of this, I mean, of the estimation of this value, then what we first want to investigate is the present, let's say, the estimation of the amplitude of the maximum and the minimum of these two-point correlation function for lensing and Doppler, and in particular in the configurations when sources are aligned and anti-aligned. And we can see that here we have that on the right panel, we have the configuration where sources are aligned, and the opposite one is on the left ones. We can see that there is a huge difference in the absolute magnitude of those values, leading to the fact that basically when these functions are extremely peaked and there is this rapid transition from
3 minutes, Giuseppe.
Almost done. Thank you. We have that this function here can be goodly approximated by a spike in the zero. And the also important aspect that I want to stress about Doppler is the transition from positive to negative values when we move across these particular scales here, which is given by just the proper value of the Hubble horizon at this redshift here. So now, just to properly, take into account the effect on nonlinear scales, then we approximate our two-point correlation function for lensing with the combination of these, let's say, two Heaviside theta function, where in particular the threshold, this angular threshold here, new threshold, is evaluated just by requiring just by imposing three physical constraints on this approximation here. First of all, that the maximum and minimum coincides with the one exactly evaluated from the analytical formulas. And secondly, this C approximated here must reproduce the fact that the monopole for the two-point correlation function of lensing must vanish, which is a fact which emerges from the exact analytical evaluations. By having this in mind, that we can immediately realize that if, in case as it is the case here, the maximum here is way larger than the minimum value of the anti-alignment, we have that this function here exactly reproduces the behavior of being extremely peaked, where nu is close to zero, and this transition scales is well described by this value of nu theta nu ij threshold. So just by then performing actively this evaluation, we come to the end of this talk, and we realize that we have that the effect for the forecasted the forecast error for the two chosen sample of LSST and EDS is at maximum of 0.2% for EDS when the sources are taken on very narrow line of sights, and becomes dramatically negligible for LSST to dropping to 0.03%. And the nice thing is that those values here are not so much affected by the taking into account of non-linearities in the Markov spectrum. And the reason for that stands in the fact that since from the structure of a statistical isotropy, this can be addressed to the exact structure which appears on the light cone when integration of the light cones are taken into account. And with that, I am done, and I thank you all for the attention.
Thank you very much, Giuseppe. So it is in time. Any question for this talk? Everything clear? Okay. So we came to the end of all the talks in this session, this last CM3 session. So before we take some time for questions, for further questions to the various speakers, I'm not sure we will have a lot of time because, as you know, there is a guillotine at the end that will cut off the Zoom connections automatically at some point. And before they do that, and before we start some discussion, in case that there is such discussion, of course, I would like to to take the opportunity to thank everybody for accepting our invitations or for just applying to this session. Everybody did great and beautifully. So I think that we learned a lot of things about these tensions, which are so exciting and which we don't know where they will lead to us in our cosmology, in cosmology, because these days are very exciting around these tensions. So we learned a lot of things, but unfortunately, perhaps we still don't know whether these problems have been solved. So there is still a lot of work to do, and in particular to see if these tensions are real or just some systematic, but we have to wait, okay? In any case, all discussions were extremely interesting, so I would like to thank to all of you for your participation. Thanks a lot. So in case that any one of you want to put a question to the speakers, if they are present, maybe not every one of them is around. I certainly have some question, but please start yourself if you have one question in mind.
Could I pose
Yeah,
a question
sure,
to
Nick,
Levon, if he's around? He is, I think. Yes.
Yeah.
Yeah. When you talk about the cosmic magnetic field, the electromagnetic energy from that is consistent with the limits, with the bounds of the cosmological constant, I guess.
Yes.
Yes, good.
I mean, magnetic fields are part of radiation.
That's right. So
they are a small fraction of the radiation density.
So you would not.
They scale like radiation.
Yeah,
as 1/8 to the 4th. Yeah.
Very good. Thanks.
More questions? Adria, you have a question? Oh, no. Or maybe.
I was looking in the participant list because I wanted to ask something to Alestas, to George Alestas, but I think he's not here anymore.
I don't think so. That's
okay,
right.
No problem, no problem.
Okay, I would like. I have a question to Levon. Actually, it's my last question concerning what is the impact on S8. Well, you have shown some contours, but I'm not sure that I understood what is the impact, because you didn't make much comment on this. You said that it goes in the right direction, but I'm not sure I understood if it is so. Can you comment more on that, please?
Yeah, so do you want to understand the physical reason why it's solved, or more about the sigmas? I mean, it brings them. So what happens is, in our model, when you relieve the Hubble tension, the physical meta density stays the same, omega meter h squared. Okay. Unlike, for example, the early dark energy models, where the best fit gives you higher physical meta density. So because the physical meta density is the same and h is larger, you get a smaller omega meta and a smaller S8. So it's
But what was the prediction of S8 in that in those contours? It was around 0.8, right? But it was the capital S8, so it means that the sigma 8 itself would be larger, I think.
I don't have. So the best way to look at these things is in a 2-parameter double contour space, where you have, let's say, sigma 8 omega meta or S8 omega meta. Because projecting them onto one axis, that doesn't tell you the whole story. So you can, what I have shown, I can try to, I closed my file, but I can try to bring it back. So,
well,
just 1 second. Oh, there. Just need to project my screen. There we go. So if I
this one,
so this plot looks more or less the same whether you show sigma 8 or S8 in terms of the tension.
Because but quantitatively, not sure.
And you can see that there is not a strong tension. This is the dark energy survey. So not kids. Obviously, the tension with kids is stronger.
Is stronger, yes.
Yeah. So we look at the most kind of mild version of the tension, which is this. And as I said, we're not really trying to solve it. We're just showing what happens to S8. So it moves it within 1 sigma agreement so that there is no tension.
Well, I'm not sure.
I mean, by
reading these numbers, you know, your prediction is clearly about 0.8, 0.25 or something like that. So, I mean, this is not a very exciting prediction for sigma 8, I would say.
Well, you should ask, what is S8 at what value of omega meta? It's not like...
No, of course. I mean, I'm looking around 0.3 or something like that.
I think it's fine. When it comes to these things, yeah, this is what it is. And you can...
Okay. No, I wanted to understand.
We can look at it from different perspectives. As far as I can see, there is no tension. I mean, yeah.
Okay. Is there any other question? Let us try to diversify the questions within the short time that we have. I still have a question for Manos, if he is around. Manos,
he's not, he's not, I think.
But he was here 5 minutes ago, or even 3 minutes ago. I checked it. So now he left.
I think he left, yeah.
Okay, I will put him a bad grade. I will tell him. I told him that I wanted to ask a question to him at the end. Okay, no problem. So in any case, if you have some other question, I don't have more now. I had 2, one for 11, another for Manos. I would like to ask Giuseppe for the future of the LSS measurements in general.
Huh. That's a very, very, very interesting question. Yeah. No, I mean, yes, in future, sorry. So now, I mean, the greatest ambition is certainly to see whether we can detect some nonlinear effects, because at the precision that we are able to achieve, this can be something which can be achieved. But in my personal view, having at disposal data which shows these nonlinearities is not only about, let's say, going to higher ordering perturbation theory, probably exact models, but it's also about having control about scale coupling, which is, I think, it's the most interesting effect which occurs when you go to nonlinear effect. So having control about this scale coupling might also be very interesting in regard of detecting, for instance, from measurement from different scales and get information about scales which are not directly accessible from observations. And this is, I think, in my personal view, is one of the most exciting things which might be achievable in the next decades. This from the observational viewpoint. If we look instead of what we are currently achieving now in numerical simulations, it's also true that now in the last years there are these relativistic n-body codes, which are at our disposal now. The first one, the most promising is G-evolution, which turns out to reveal a lot of interesting nonlinear features, even in the distribution of, let's say, luminosity distance redshift relations, which is and those features which we can detect are not only nonlinear but exhibit also strong non-Gaussianities. For instance, in the distribution of the nonlinear, in the distribution of luminosity distance redshift relations. And I think that if we manage to have a theoretical control, let's say even perturbative schemes about having control about those non-Gaussianities, might be also a very interesting things to investigate in the actual future, because it's something that we want to definitely have control about to constrain dynamical models nowadays.
Okay, thank you very much. Maybe there is time for the last question. They are about cutting off, I guess. Yes, sure. Sebastian, please.
Yeah, I would like to ask to Nikolaos, to Nick Mavromatos.
Yes.
The question is the following. Could you, for example, motivate the appraisal of the Gauss-Bonnet term and then turn into a field the coefficient that appears
in our approach? We don't have, yeah, you mean the anomaly term, because the Gauss-Bonnet is different. You mean the Chern-Simons term?
Yeah.
Or the Gauss-Bonnet you want?
I want the Gauss-Bonnet. I mean,
the Gauss-Bonnet, okay, which I did not discuss. The Gauss-Bonnet comes because in string theory, if you view this cosmology as a result of some string theory model, you have higher order terms in derivatives. So the Einstein term always is corrected in addition to the Hilbert space by some higher curvature terms. The first order non-trivial order in derivatives, because of general covariance, you have to have even number of derivatives and of curvature tensors, or covariant derivatives of curvature tensors. So the first one is the Gauss-Bonnet, which is actually the perturbative spectrum of string has to be ghost-free, because if you don't have the Gauss-Bonnet, in the propagator of gravitons have ghosts. You can check that. So the Gauss-Bonnet, of course, in 4 dimensions, the Gauss-Bonnet is total derivative, but coupling it to dilatons, which is the string coupling, you get the non-trivial term. So the motivation comes because the effective action in strings have higher curvature terms, is a modified gravity, and is ghost-free the spectrum. So by field definitions, you always cast it in a Gauss-Bonnet, even in any dimension. So in any higher dimensional thing where the Gauss-Bonnet is non-trivial, you need a ghost-free action, and by field redefining the matrix, which leaves the scattering matrix, the perturbative scattering matrix invariant, you get the Gauss-Bonnet. Is that clear enough for your question, or?
Not really. I mean, you have considered the R tilde R.
Oh, for us, it's not the Gauss-Bonnet. That's what I said. It's the Chern-Simons.
Yeah, that's a
anomaly.
Chern-Simons.
Yeah.
It's Chern-Simons. That's what I asked before.
That's a Chern-Contragin term. Yeah.
Okay, fine.
But
so the R tilde comes because.
No, sorry, but
no problem. That's what I asked at the beginning.
The question is, I mean, do you have considered also the Gauss-Bonnet term?
Yes, you can actually simultaneously. You can do it, but the Gauss-Bonnet doesn't do the effects that we are talking about. The reason of an anomaly is because you have anomalies. If you have gravitation in string theory, in principle, you have gravitational anomalies because you have chiral fermions circulating in the loops in 4 dimensions. Now, in string theory, you have a cancellation, if you like, in the extra dimensions, because in the original string theory, people were thinking only of cancelling anomalies in the extra dimensions, not in the 4-dimensional thing. So they were matching the gauge field in the bulk, in the extra dimensional sector with the FF tilde with the RR tilde. These are both 2 Chern-Simons terms. In our, however, and in order to cancel these anomalies, you have to add the so-called Green-Schwarz counterterms, which appear in the definition of the field strength of the B, of this action, of this spin of the Karl-Bramon action, which is the ground state, is a field in the ground state multiplier of the string, of the massless multiplier of the string, of the superstring, or in the massless multiplier of the bosonic string. then because of these grants, if you remember the Chern-Simons terms there, had such a form that when you take there is a Bianchi identity when you consider this field strength, and when you implement this Bianchi identity in a path integral, you implement it via a Lagrange multiplier. And it turns out, because of these extra modifications in the DAs, that you have the Chern-Simons term, the RR tilde, coupled to the action minus FF tilde coupled to the actions. But in our case with Joan, in our model, we assume that the external fields it's only gravitational fields. That's an assumption. And then the gauge fields appear at the exit of inflation. So the the Chern-Simons term appears because you don't cancel the gravitational anomalies versus the gauge anomalies in the four-dimensional sector. And that's still consistent with the diffeomorphism invariance. There's nothing wrong with that. Is that clear now, or?
Not easy to explain this.
Not easy. I have to. It is okay. Think of the actions. Okay, the actions coupled to FF tilde. You are familiar with this, I suppose. Yeah. It's the analog of the electric times magnetic field times an action, right? An action couples to EB terms. There is an electric field dot magnetic field times an action. The analog of the electric field times magnetic field for the gauge sector is this anomaly, is this CP violating gravitational term. They are both terms of CP violating. That's why, but it is implemented by a constraint. I don't know if Joan wants to say something or more on this, or someone.
Still, yeah.
I don't know. Is that clear? I mean, is it? It comes about because you have uncancelled anomalies, gravitational anomalies in the spectrum of four-dimensional strings, which are still consistent with diffeomorphism invariance. It just express an energy change between the action and the gravitational field.
If you want, another question would be,
please.
Is